Hello and welcome to this revision session for AQA A-Level Physics on the topic of electricity, which is found in paper 1 on current, resistance and resistivity. So if we've been successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show the full working out. Now in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So for some tips for your revision, how can you be independently revising A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, prep notes in the textbook to learn the key ideas of the course. You may wish to make mind maps or write out the notes yourself. Secondly, test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge. You may wish to do this from your own cue cards. Then finally, step 3 is to practice. Use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. So you may wish to download your own exam past papers to do this. So you should be doing the 3 steps of learn the key facts, testing yourself and practicing exam style questions. Now in this revision session we're going to be looking at 2 types of questions, key check questions and then examination style questions. So let's have a look at these key check questions. So to assess your understanding for all of these questions, they're short, sharp questions which will test your key knowledge. So look at the following. What is the current in this circuit and how is the current produced? So pause the video now, then unpause the video when you want to go through your answer. Now current is the flow of electrons around the circuit due to a voltage acting across the circuit. Now what is producing the electromotive force in the circuit to cause a current? Pause the video now, then unpause the video when you want to go through your answer. Well, the battery or the power source and the outer charge of the wire produces an electromotive force to produce a current. The next question. Why does the power source not produce an electromotive force when it is not switched on? So pause the video now, then unpause the video when you want to go through your answer. Right, the power source produces an electrical field when it's turned on. So when switched off, the overall electrical field produced by the power source is 0, so you're not going to get an electromotive force. The next question says, what is the size of the current in this circuit? And what does this tell you about the free electrons? So pause the video now, then unpause the video when you want to go through your answer. Well, in a series circuit, the current is constant. So this means that the free electrons are moving through the circuit at a constant rate. The next question says, why is the current constant in a series circuit? So pause the video now, then unpause the video when you want to go through your answer. Right, the current is constant as the electromotive force in the circuit is constant as the power source and wires are producing a constant electrical field when switched on. The next question says, why do bulbs turn on immediately when the circuit is complete? So pause the video now, then unpause the video when you want to go through your answer. Right, there are free electrons everywhere in the circuit and there are electrons immediately where the bulbs are. So we'll move through it almost instantly. The next question says, why do the bulbs light up when electrons move through them? So pause the video now and unpause the video when you want to go through your answer. So the free electrons will collide with the metal ions in the bulb. This dissipates the electrical energy as thermal energy and this heats up the filament, causing it to glow. The next question says, if the power source is provided the circuit with 12 volts, what should the overall potential difference of the bulbs combined be and why? So pause the video now, unpause the video when you want to go through your answer. Right, the combined potential difference should be 12 volts as electrical energy is conserved in the circuit. The next question says, in reality, why will the combined potential difference of the two bulbs be less than 12 volts? So pause the video now, unpause the video when you want to go through your answer. Right, as the electrons travel through the circuit and the power source, they will collide with their ions, causing the energy to be dissipated from the circuit before it reaches the bulbs. The next question says, could an electrical current of protons be produced, and why? So pause the video now, then unpause the video when you want to go through your answer. Right, yes it could, because protons are charged and the electrical field of the power source and wire will interact with any charged particles placed inside of it. The next question says, what is resistance in the circuit and how is resistance produced? So pause the video now, then unpause the video when you want to go through your answer. Right, resistance is the impedance to the flow of charge in an electrical circuit. It's produced by the collisions between electrons and ions in the material that they are moving through. The next question says, what is the link between resistance and the length of the material and why? So pause the video now, then unpause the video when you want to go through your answer. Right, the resistance and the length of the material are directly proportional. As the longer the material the electrons travel through, the greater the number of collisions between the electrons and the ions. The next question says, what is the link between resistance and the cross-sectional area of the material and why? So pause the video now, then unpause the video when you want to go through your answer. Right, the resistance and the cross-sectional area of the material are inversely proportional. As the greater the cross-sectional area of the material, the lower the density of collisions between the electrons and the ions, lowering the resistance. The next question says, what is the link between resistance and the temperature of the material of a conductor and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the resistance and the temperature of the material of the conductor are proportional. The greater the temperature, the greater the amplitude of vibration for the ions, the greater the number of collisions, so the greater the resistance. The next question says, what happens to the resistance of a bulb as it is being used and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the resistance of the bulb increases as the temperature of the bulb increases as it is being used. The next question says, why does a filament bulb not follow Ohm's law? So pause the video now and unpause the video when you want to go through your answer. Well, the filament bulb does not follow Ohm's law as the resistance does not stay constant over its operating voltage because it is heating up. Now the next question. What is the link between the resistance of a material and its output potential difference, and why is this? So pause the video now, then unpause the video when you want to go through your answer. Right, the resistance and the output potential difference are directly proportional. As the greater the resistance, the greater the energy dissipated through the device, the greater the potential difference of the device. The next question says, what is a superconductor and how is this achieved? So pause the video now, unpause the video when you want to go through your answer. A superconductor is a device with no resistance as there are no collisions between the electrons and the ions of the conductor. So why is there no resistance when a current is not flowing in a circuit? So pause the video now, then unpause the video when you want to go through your answer. Now, when there is no current, the electrons still move in random directions and collide with ions. However, there's no direction they should be moving in, so no impedance to the movement in a direction. The next question says, looking at the two wires, which would generate the larger resistance for the same potential difference and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the larger the wire, the more you would generate a resistance for the same potential difference, because there are more ion charge carrier collisions as the wire itself has more ions. Now, both of these wires are made from copper. Would they have the same resistivity for the same potential difference, and why? So pause the video now, then unpause the video when you want to go through your answer. Right, they would have the same resistivity as they are the same material, and the resistivity is independent of the length and the cross-sectional areas of the objects. Now, both wires are heated. What would happen to their resistivities and why? So pause the video now, then unpause the video when you want to go through your answer. Now both resistivities would increase, as increasing the temperature increases the amplitude of ion vibration in the wire, so there'd be a greater frequency of charge carrier ion collisions. Now when A is double the length of B, what would the difference in their resistances be and why? So pause the video now, then unpause the video when you want to go through your answer. Well, wire A would have double the resistance of wire B, as resistance and length of a wire are directly proportional. Now wire A is double the length of wire B. What would the difference in their resistivities be and why? So pause the video now, unpause the video when you want to go through your answers. Well, the two wires would have the same resistivities as they are made of the same material. Now, how can wires have different lengths but the same resistivity? So pause the video now, then unpause the video when you want to go through your answer. Now, as the length of the wire changes, the resistance of the wire also changes to ensure that the resistivity of the material stays constant at all times. So, what is the relationship here between the cross-sectional area and the resistance of a wire, and why? So pause the video now, then unpause the video when you want to go through your answer. Now, as the cross-sectional area of a wire increases, the resistance decreases. They are inversely proportional, as the charge carriers are more spread out in the wire, so there is a smaller frequency of collisions with the ions of the wire. Now, what is the relationship between cross-sectional area and the resistivity of a wire, and why? So pause the video now, then unpause the video when you want to go through your answer. Now, the resistivity and the cross-sectional area of a wire are not dependent on each other, as the resistivity of a material is constant for the same temperature. So now we've looked at the general check questions on this concept, let's have a look at some exam-style questions. So to start us off, describe the difference between resistance and resistivity. Calculate the resistance of a copper wire of length 1.0 meters and a cross-sectional area of 3.32 times 10 to the minus 6 meters squared, where the resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Explain the effect of changing the temperature on the resistivity of a metal, and calculate the resistivity of a piece of wire when it has a resistance of 170 ohms, when it has a length of 12 meters and a radius of 3 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, so the difference is that resistance applies to a particular component, whilst resistivity is a property of the material itself. In the next question, resistance is equal to resistivity times by length over area. Now you're given all the values in the question, so you pop them into the equation, and it's 5.1 times 10 to the minus 3 ohms. Now when the temperature of a metal is increased, it's a conductor, the positive ions in the metal have more energy. So the positive ions will vibrate with a greater amplitude. You'll get a greater frequency of charge carrier and ion collisions, so therefore the resistivity has increased. Now this next question is going to be a bit harder. Now firstly, you need the area. So the cross-sectional area is pi r squared. Now we've got to change our radius of 3 millimeters into 3 times 10 to the minus 3 meters. We assume it's a circular cross-section, so therefore it's pi r squared, so it's 2.82 times 10 to the minus 5 meters squared. Now resistivity is resistance times by area over length. Pop in all the values, work it through, and it's 4.0 times 10 to the minus 4 ohm meters. The next question says, the critical temperature of tin is minus 269 degrees Celsius. The resistivity of tin increases as the temperature rises from minus 269 degrees Celsius. Define the resistivity. State the significance of the critical temperature of a material, and a sample of tin in the form of a cylinder of diameter 1 millimeter and length 4.8 meters has a resistance of 0.70 ohms. Use this data to calculate a value for the resistivity of tin. State an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so the definition of resistivity, it can be done in two ways. You could state that resistivity is the property that describes the extent to which a material opposes the flow of an electrical current going through it. Or you could say it is the value of resistance generated for a length of 1 meter and a cross-sectional area of 1 meter squared. Don't forget to use the word cross-sectional area. Now the critical temperature is one where below the critical temperature you will get no resistivity or resistance, and the device becomes a superconductor. Now in the next question, we know that resistivity is equal to the resistance times by the area over the length. Now again, to work out our area, we assume, because the cross-sectional area is pi r squared, it's a circle, the diameter needs to be halved to get to the radius, and we need to convert our millimetres into metres. So when you work it through, you get 1.15 times 10 to the minus 7 ohm metres. The next question says, sketch a graph of I against V for a metallic conductor at a constant temperature and use it to describe Ohm's law. The current in a resistor is 0.50 amps and the potential difference across it is 5.2 volts. Calculate its resistance. Define the ohm and express it in base units. Then a length of wire is connected to a cell. The current in the wire is 80 milliamps and the PD across the wire is 2.4 volts. Calculate the resistance of the wire. Then a resistor has a resistance of 1.2 kilo ohms. In 3 minutes, a charge of 54 coulombs flows through the resistor. Calculate the potential difference across the resistor. Then finally, the current in a filament lamp is 1.5 amps. It is operated for a time of 1 minute. The charges flowing through the lamp transfer 500 joules of energy to the lamp. Calculate the resistance of the lamp. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we should know that for a metallic conductor, I against V is a straight line through the origin, because V is directly proportional to I for a conductor at constant temperature. That is Ohm's law. Resistance is V over I, you should be aware of that. So pop the values in, you get 10 ohms. Now you can define the ohm in terms of the equation, R equals V over I. So 1 ohm is the resistance of a component where a potential difference of 1 volt is produced per 1 amp of current. Now you can work through your base units, so 1 ohm is 1 kilogram meter squared, seconds to the minus 3, amps to the minus 2. In our next question, once again, R equals V over I. Now remember, milliamps have to turn into amps, so it's 80 times 10 to the minus 3. So we get our answer to be 30 ohms. In our next question, we've got to use multiple equations. So we know that I equals Q over T. Now again, time should be in seconds, not minutes. So 3 minutes becomes 180 seconds. 54 over 180 is 0.30 amps. V equals IR, 0.3 times by 1200 kilo ohms into ohms. So you work it through to be 360 volts. And it's the same for the next question. We know that V is equal to the work done over the charge. Now charge is equal to IT. So therefore it's 500 over 1.5 times by 60 because we don't work in minutes, we work in seconds. So we get 5.55 volts. R equals V over I. We've got V, we've got I from the question. So you work it through to be 3.7 ohms. Now our next question is an examination style question. So in a research facility, engineers are working with an experimental superconducting transmission cable. The cable is cooled using liquid helium to below its critical temperature, allowing current to flow with zero resistivity. The cooling system uses negative temperature coefficient thermistors as sensors embedded along the cable to monitor temperature changes. These sensors are connected to a control system that adjusts the flow of the coolant. Occasionally, the engineers notice sudden non-linear fluctuations in the resistance readings of the thermistors and an unexpected increase in the energy loss in the cable. So discuss the physical principles that could explain why the thermistor resistance varies with temperature and how this property makes it useful in this context. Suggest what might cause the non-linear fluctuations in resistance observed during operation and explain how they could be related to the behavior of the superconducting cable. Then discuss the advantages and practical challenges of using superconducting materials in power transmission systems like the one described. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know that NTC thermistors have a resistance that decreases as temperature increases. Now this is due to the increased availability of charge carriers or electrons into the circuit as the temperature rises. So this allows for an accurate monitoring of small temperature changes near the critical temperature, which is what is needed for this context. So in the cryogenic system, this enables the automatic control of the coolant to maintain the superconducting conditions required. Now for the next question, the fluctuations can indicate to you that the cable temperature must be approaching or even exceeding the critical temperature. Now exceeding the critical temperature is important as it will cause the material to lose its superconductivity and again it will regain resistivity, resulting in some energy loss. Then the thermistor's non-linear response could be due to the fact that there's a change in thermal environment, that the temperature changes rapidly, or that there's a feedback system delay when you're using the thermistor. Now in the last part of the question, superconductors, you've got to be aware, eliminate resistive losses, allowing for extremely efficient power transmission. They can also generate strong magnetic fields without energy losses, but the challenges include maintaining very low temperatures, it's very expensive, and it's unstable near the critical temperature itself. So the next question says, a surveillance drone is designed to operate at very high altitudes, where ambient temperatures fall below minus 60 degrees Celsius. The onboard electronics are protected by an automatic heater system triggered by an embedded NTC thermistor. On the ground, where the temperatures are much warmer, the thermistor has a resistance of 1,800 ohms. At altitude, when the drone stabilizes in very cold conditions, the resistance of the thermistor increases to 4,000 ohms. The thermistor is wired in a circuit with 1,200 ohm resistor and a 12-volt battery supply. When the voltage across the thermistor rises above a certain threshold, the heater activates. So explain how the use of an NTC thermistor in this system ensures that the heating is activated only under low temperature conditions. Given that the change in resistance is from 1,800 ohms to 4,000 ohms, discuss what happens to the voltage across the thermistor and whether this will cause the heater to activate. And then suggest one limitation of using this type of resistance-based switching system in an environment with rapid temperature changes or electrical noise. So pause the video now. Then unpause the video when you want to go through your answer. Right, in this first one, once again, we're looking at how a thermistor works. So as a thermistor's resistance increases as the temperature decreases. So this means, in this context, as the temperature drops, the increased resistance affects the voltage across the thermistor. Now this voltage can be used as a signal to activate the heater, ensuring it only turns on when it's cold. Now in the next question, on the ground, the lower the resistance of the thermistor means the voltage across it will be lower, because we know V is proportional to R. Now at high altitudes, the thermistor's higher resistance causes the voltage across it to increase. So the increased voltage indicates that the system must be cooler, because we know the link with resistance. So if the voltage rises past a predetermined trigger level, the heater will then be activated. So therefore the change in resistance going from 1,800 ohms to 4,000 ohms suggests that the voltage has increased significantly because the temperature has dropped significantly, triggering the heater to work in colder conditions. So you've got to link how a thermistor works to the actual context of the situation. Now in our last part, the system could be sensitive to small fluctuations in resistance due to electrical noise interference or instability in rapidly changing conditions. So this could cause the unintended activation or a failure to trigger the heater at the correct temperature, which would mean it wouldn't work as appropriate. The next question says, a new carbon composite material is being tested for use in remote infrastructure monitoring systems. The material forms part of a sensor cable embedded in concrete. Engineers expect the resistance of the sensor cable to change with both temperature and strain, allowing them to monitor structural integrity and environmental conditions. Now a section of the cable has a uniform length of 1.50 meters and a diameter of 2.00 millimeters. At a baseline temperature of 20 degrees Celsius, the resistance is measured to be 12.8 ohms. On a hot day, the resistance rises to 15.2 ohms when the ambient temperature is 45 degrees Celsius. The material has a temperature coefficient of resistance alpha, which is equal to 3.2 times 10 to the minus 3 Celsius to the minus 1, where we know that the resistance at a certain temperature is equal to the baseline resistance times by 1 plus the coefficient temperature times by the change in temperature. Now again, this equation isn't given to you or expected to be learnt, in your exam, but you can use it because they've given it to you in this question. So, calculate the resistivity of the material at 20 degrees Celsius, determine the resistance expected at 45 degrees due to the temperature alone, and compare your result with the observed resistance and comment on what this suggests about the sensor cable, and then suggest one reason why the resistivity of this composite may not behave identically to that of a pure metal over wider temperature ranges. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out resistivity. First thing we need to do, work out the area. We assume the cross-sectional area is a circle, so it's pi r squared. So we get our diameter, we half it, we turn it into meters, so we get 3.14 times 10 to the minus 6 meters squared. We know that resistivity is resistance times by area over length. We have all the values now, so it's 2.68 times 10 to the minus 5 ohm meters. Now in this next one, we've got to use the equation given to us in the question. We know that the change in temperature is 45 minus 20. It's going from 20 to 45, so the change is 25. So therefore, the resistance at 45 degrees is 12.8 times by 1 plus 3.2 times 10 to the minus 3 times by 25. So it's 12.8 times by 1.08, which is 13.82. Now the observed resistance in the question is given to be 15.2 ohms. So the resistance observed is greater than the temperature alone. So therefore it suggests that the sensor cable must have experienced strain, it's stretched out, there's been a dimensional change, it's increased its length, so the resistance has gone up. Now the last question, composites, often include insulating phases or irregular structures that can affect charge flow. So this can lead to non-linear or unpredictable resistivity changes with temperature, unlike the predictable behaviour of pure objects. The next question says, an engineer is designing a compact power supply unit for an experimental sensor array. The design requires a current limiting component that adjusts the flow of current depending on the operating conditions, including changes in ambient and internal temperatures. To assist with the component selection, the engineer examines the current voltage characteristics for 3 components under test conditions: a metal wire kept in a thermally regulated housing, a filament lamp, and a semiconductor diode. A summary of the behaviour is observed. Component X, the current increases proportionally with voltage over the measured range. Component Y, the current initially rises but begins to level off as the voltage increases. Component Z, little current flows until a certain voltage is reached, after which the current increases rapidly. So identify each component and explain the physical reason for the behaviour observed in each case. Discuss the limitations of applying Ohm's law to each of the 3 components in this context. Then the engineer selects component Y for current limiting protection against overheating. Evaluate this choice, and in your answer consider how the electrical behaviour of the component responds to change in physical conditions and whether it's suitable for this role. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one, what do we know? Well, component X is the metal wire. There's a linear IV relationship indicating a constant resistance, or it follows Ohm's law. This is because the metal is temperature controlled, so it keeps the resistivity constant. Component Y is the filament lamp, because the current increases more slowly at higher voltages because there's an increasing resistance. This is due to the heating of the filament, which increases the resistivity. Whilst component Z is the semiconductor diode. There's a very low current until the threshold is passed, then the current increases sharply. So it's caused by its structure, which permits conduction only after the forward bias voltage is reached. Now, the next one, you can understand that Ohm's law only applies to constant physical conditions and the fact that I is proportional to V. Now, only the metal wire will satisfy this since the temperature is kept constant. Now, the lamp and the diode are non-ohmic because their resistance will change with temperature or voltage. So in their cases, Ohm's law does not apply. Now, finally, the filament lamp, which is component Y, increases in resistance with temperature, so it naturally will limit the current as it heats up because the resistance is increasing. So this can protect the circuit by reducing the current flow under the high temperature conditions. Whilst it's not particularly precise or accurate, it is practical and it's a good passive method for protection, so it's suitable where you don't need a complex control system. The next question says, a design engineer is testing a battery-powered heating element using a medical emergency kit. The element is activated for 45 seconds to warm a gel pack. A microcontroller records the following measurements during the activation period. A steady current of 2.4 amps flows through the element. The potential difference across the element is 6 volts. The total energy transferred to the gel pack is recorded as 650 joules. After reviewing the data, the engineer suspects that either the current or the energy reading may be inaccurate and decides to investigate further. Firstly, define electrical current and potential difference in terms of fundamental quantities. Using the data provided, determine whether the energy reading is consistent with the values of current, potential difference and time, and show your reasoning. Determine the resistance of the heating element during operation, and then the engineer suggests that the energy reading may be too low due to the internal resistance within the battery. Evaluate this suggestion using relevant physical principles to support your conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to know how to define key terms. So electrical current is defined as the rate of flow of charge. I is equal to change in Q over change in T. And potential difference is the work done per unit charge. or V is equal to W over Q. Now we know from the information provided that the power is equal to voltage times by current, so it's 6 times by 2.4 from the information given to you, so that's 14.4 watts. Now energy transferred is power times by time, so it's going to be 14.4, what we just calculated, times by 45 seconds, so it's 648 joules. Now given that the value stated in the question 650 joules, that's very close to the calculated value, indicating that yes, the energy reading is consistent with the current and the potential difference. In our next question, we know R equals V over I, so it's 6 over 2.4, so it's 2.5 ohms. And then finally, if the battery had an internal resistance, well then the terminal voltage will be lower than the EMF when the current flows. So this means the external circuit would receive less energy than expected from the EMF alone. However, in this case, the measured energy actually matches the calculated value from the terminal voltage times by the current times by the time. Therefore, in this case in particular, the suggestion is unlikely because the internal resistance would cause a discrepancy in the energy reading, which is not really observed here. The next question says, an engineering team is testing a prototype wearable heating vest designed for mountaineers. The vest uses resistive heating mesh powered by a rechargeable lithium battery. During testing, the team records the following data. A steady current of 1.5 amps flows through the heating mesh. The potential difference across the mesh is 4 volts. The battery's rated energy capacity is 15 kilojoules. Users report that the vest only stays warm for 22 minutes despite expectations of at least 30 minutes of heating. An internal report concludes that the issue itself lies in inefficiency energy use or thermal losses elsewhere in the circuit, not with the heating element itself. So determine whether the duration of the heating reported by users is consistent with the energy transfer to the heating mesh based on the data provided. Show your reasoning. The team wants to reduce power consumption without changing the battery. Suggest and justify one electrical change to the circuit design that could extend the heating time and discuss a potential trade-off in performance. Then finally, evaluate the claim made in the internal report that the underperformance is not due to the heating mesh but to inefficiencies elsewhere in the system. In your answer, consider both electrical and thermal processes. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, let's work out the power delivered to the mesh. P equals VI, 4 times by 1.5, it is 6 watts. Now the energy used over 22 minutes is therefore E equals P times by T. So it's 6 times by 1320, which is the number of seconds in 22 minutes. So it's 7.92 kilojoules. Now the expected maximum usage with full energy, we know is going to be time, is going to be equal to 15,000, the energy capacity, over 6. Okay, which is going to be the power, so that's going to be 2,500 seconds, which is 41.7 minutes when you work it through. So what that tells us is that the heating vest only heats for 22 minutes, much less than the theoretical value. So therefore, the significant energy is not being delivered to the mesh, which is needed for it to work, so support that there must be a loss elsewhere. Now, how could you then reduce the power consumption without changing the battery? So you've got to think of a suggestion of reducing the current. So you could think about increasing the resistance of the mesh to reduce the current whilst keeping the voltage of the battery the same. So this will reduce the power, because we know P equals I squared R. So therefore P will drop if I drops. So the energy will therefore last longer. So therefore there'll be a lower power over time. So the trade-off is that there'll be a lower heat output, so the user will feel less warmth, reducing the perceived effectiveness, but it will occur for that at least 30-minute time period. Now in the final question, the heating mesh appears to work as expected based on its calculated power consumption. Now if the heating time is shorter than the battery capacity allows, energy must be being lost or diverted elsewhere. So the likely sources could include internal resistance in the battery, energy loss as heat in connecting wires, in the control electronics, or poor thermal insulation. Now some energy may also be lost in regulation or control circuits or lost via heat escaping from the vest. So overall, you can conclude that the claim itself is plausible. The data supports that the energy losses occurring upstream or downstream of the mesh, but not in the mesh itself. Our next question says, state what is meant by the EMF of a battery, and figure 10 shows the circuit diagram for a battery powered torch. The circuit contains 3 identical light emitting diodes and a resistor R. The current in the circuit is 44 milliamps. Calculate the number of electrons that pass a point in the circuit in 37 minutes. So pause the video now, then unpause the video when you want to go through your answer. Right, we got to learn the definitions of key terms. So EMF is the amount of chemical energy transferred or amount of energy converted to electrical energy for 1 coulomb of charge. It's per coulomb of charge. Now our next question, we know that charge is equal to current times by time. Time has to be in seconds though, so 37 minutes turns into 2,220 seconds by doing 37 times by 60. Remember, 44 milliamps turns into amps, so you get 97.68 coulombs. So the number of electrons is 97.68 divided by the charge of one electron, 1.6 times 10 to the minus 19 coulombs, 6.1 times 10 to the 20 electrons. Our next question says, a student was given a block of conducting putty of mass 43 grams. Show that the volume of the conducting block was about 8 times 10 to the minus 6 meters cubed. The density of the conducting putty is 5,300 kilograms per meter cubed. The student formed the putty into a cylinder. Coins are pushed onto the ends of the cylinder as shown. The coins each had a crocodile clip attached and an ohmmeter connected across the putty. Determine the resistance of the cylinder of the putty. So the diameter of the cylinder is 12 millimeters. The resistivity of the conducting putty is 4 times 10 to the minus 3 ohm meters. And then the student made a cylinder that had a large resistance. How could the student use the putty to make a larger resistance? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that volume is mass over density. So we turn our grams into kilograms, so 0.043 kilograms over the density of 5,300. So it's 8.1 times 10 to the minus 6 meters cubed. In our next question, we can work out our area, because area is pi r squared because it's a cylinder, so the cross-sectional area will therefore be a circle. So you can work it through, remembering to turn any diameter into a radius and the millimeters into meters. So you can get 1.13 times 10 to the minus 4 meters squared. Now we've got an area, we've been told a volume, so therefore we can work out a length, which is needed for the resistance equation. So what we can therefore do is say that the length is equal to the volume over the area. So the length is 0.0716 meters. Pop that into the equation. That resistance is equal to resistivity times by length over area to get 2.54 ohms. Now finally, how could you make a larger resistance? Well, you make the cylinder of a longer length, or the cylinder of a smaller radius or area, because from the equation R equals rho L over A, a longer length or a smaller area will change the resistance to increase it. So that brings an end to our revision session today. If we've been successful and learnt in today's revision session, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on AQA A-Level Physics, Paper 1, Electricity, focused on the topics of current, resistance and resistivity. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics on Paper 1 in the topic of electricity, and we're going to be looking at potential dividers and internal resistance. So in today's revision session, if we've been successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics and understand what topics we need to improve upon for AQA A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show the full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. At the end of this revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and the textbook to learn the key ideas of the course. Now, you may wish to make mind maps or to write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca and knowledge checkers to quickly test your own knowledge. Now, you may wish to do this from your own cue cards. Finally, use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. Now, you may wish to download your own examination past papers to do this. So our three areas of learning the key facts, testing yourself, and practicing exam style questions are how you should revise for A-Level Physics. Now, in this revision session, we're going to be focusing on two types of questions. Firstly, our general or key check questions, which are basic questions designed to probe your understanding of the key concepts of the topic. Then we're going to look at assessment point questions, past paper examination questions, which will mimic the type of questions found in public examinations. So let's have a look at these general check questions. The first question says, what is a potential divider? So pause the video now, then unpause the video when you want to go through your answer. Well, a potential divider is a circuit with two or more outputs on a single path, and this will split the potential difference between the two outputs. The next question says, what determines the potential difference across an output? So pause the video now, then unpause the video when you want to go through your answer. Well, the proportion of total resistance that the output has determines the potential difference that the output will have. The next question says, in a potential divider, what do you know about current and why? So pause the video now, then unpause the video when you want to go through your answer. Well, a potential divider is a series circuit, so therefore the current is the same throughout the circuit and across the outputs due to Kirchhoff's first law of electrical circuits. The next question says, what is the effect of loading a potential divider on its output voltage and why? So pause the video now, then unpause the video when you want to go through your answer. Well, loading a potential divider is placing many outputs in parallel on the useful rail of the potential divider. So this will decrease the resistance of the outputs as they're in parallel, so will decrease the useful output voltage. The next question says, what is another name for the useful output voltage of a potential divider circuit? So pause the video now, then unpause the video when you want to go through your answer. Well, another name for the useful output voltage is called the tapping off voltage. The next question says, what is the equation used to work out the voltage output of a potential divider and where does it come from? So pause the video now, then unpause the video when you want to go through your answer. Well, V out is equal to R2 over R1 plus R2, the total resistance, times by the input voltage. Now this occurs because V is directly proportional to R in a series circuit because the current is constant. The next question says, how can a light sensor be made from a potential divider? So pause the video now, then unpause the video when you want to go through your answer. Well, a light sensor can be made by using an LDR as one of a number of outputs placed in a series circuit. The next question says, what is a potentiometer? So pause the video now, then unpause the video when you want to go through your answer. So, a potentiometer is a potential divider containing a variable resistor instead of two resistors in series. So what this means is it has three connectors in the circuit. The next question says, why does loading the potential divider decrease the useful output? So pause the video now, then unpause the video when you want to go through your answer. Well, it's because the equivalent resistance in the lower rail or useful rail of a potential divider is now a parallel combination of R1 and R2. So it'll be less than what it was before you placed the other device in parallel. So therefore, there's a smaller value of resistance, so a smaller fraction of the potential difference is now tapped off by the useful outputs. The next question says, when does the effect mentioned previously take place? So pause the video now, then unpause the video when you want to go through your answer. Well, this will happen if R2 is much greater than R1, because when that's the case, there's no significant effect on the output potential difference, as adding a large resistance in parallel in fact gives a small addition. So, for the effect to actually take place, the resistance in each output must be similar. R1 must be approximately equal to R2 for this effect to take place. The next question says, what causes lost volts in a circuit? So pause the video now, then unpause the video when you want to go through your answer. So lost volts is the energy per unit charge, which is the definition of volts, lost in the circuit due to internal resistance generated by the power source and the electrical wires of the circuit. The next question says, what produces internal resistance in a battery? So pause the video now, then unpause the video when you want to go through your answer. Well, a battery provides work to move a charge by a chemical reaction. So the internal resistance is when the energy, such as heat, is generated in the chemical reaction. The next question says, what produces internal resistance in the wires of the circuit? So pause the video now, then unpause the video when you want to go through your answer. Well, a wire provides internal resistance due to the collisions between the charged particles and the metal ions as the charged particles flow through the metal wire. The next question says, what is Kirchhoff's law, second law, when considering internal resistance, and what is conserved in this? So pause the video now, then unpause the video when you want to go through your answer. Well, from Kirchhoff's second law, we can say that the EMF into the circuit is equal to the terminal PD out of the circuit plus the lost volts out of the circuit. Now this is, from all of Kirchhoff's second law, the conservation of energy in the electrical circuit. So, the next question says, what would the effect of a small internal resistance have on a circuit? Would this be efficient, and why? So pause the video now, then unpause the video when you want to go through your answer. So, a small internal resistance would lead to a large current flowing in the circuit itself. Now this would lead to actually an inefficient circuit, as lots of the energy will be dissipated in the load resistance, the resistance of the output circuit. The next question says, what would the effect of a high internal resistance have on a circuit? Would this be efficient, and why? So a high internal resistance would lead to a low current flowing in the circuit. This would lead to an inefficient circuit, as lots of energy will be dissipated in the internal resistance of the circuit. So, the final question on this aspect is, when is an electrical circuit at its most efficient, and why? So pause the video now, then unpause the video when you want to go through your answer. An electrical circuit is at its most efficient when the internal resistance equals the load resistance, as the internal resistance will lower the current to a reasonable value where it will not dissipate much energy through the load resistance of the circuit. The next question says, when does the terminal PD equal the EMF, and why? So pause the video now and unpause the video when you want to go through your answer. So the terminal PD will equal the EMF when there's no current flowing in the circuit, as there can be no internal resistance in the circuit when no current is flowing, so there can't be any lost volts in the circuit. The next question states, how can a voltmeter measure the EMF of a power source, and why? So pause the video now, then unpause the video when you want to go through your answer. Well, in this aspect, the voltmeter can measure the EMF of a power source if it's connected directly and only to the power source, as the voltmeter has an infinite resistance, so no current can flow through the circuit, so there can't be any internal resistance. The next question says, if the internal resistance of a circuit is fixed and the current through the circuit is increased, what happens to the EMF, and why? So pause the video now, then unpause the video when you want to go through your answer. The EMF stays fixed as it's provided by the power source only, so it's not going to be affected by the current of the circuit. So, if the internal resistance of a circuit is fixed and the current through the circuit is increased, what will happen to the terminal PD, and why? So pause the video now, then unpause the video when you want to go through your answer. The terminal PD of the circuit will drop as the current increases, as the internal resistance through the circuit will generate a greater value of lost volts, so it will decrease the output or terminal potential difference of the circuit. Our next question says, why does a battery short-circuited not produce infinite current? So pause the video now, then unpause the video when you want to go through your answer. The battery will have an internal resistance, as it is being short-circuited. So this will limit the short-circuit current to a maximum value and not an infinite value. Now, to assess our understanding, a 270 ohm resistor and a 170 ohm resistor are connected as part of a potential divider circuit to a 36 volt supply. The output is connected across a 270 ohm resistor. Calculate the output voltage. Then outline how a pair of identical resistors can be used in a potential divider to produce an output of 10 volts from a 20 volt supply. Include a labelled diagram in your answer. And then finally calculate the output voltage from the two potential dividers below. So pause the video now, then unpause the video when you want to go through your answer. Well, in this first one, we've got to use the potential divider equation. So V out is equal to R2 over R1 plus R2 times by the input voltage. So that's 270, the second resistor, over the two values added up, times that by 36 is 22 volts. Now our circuit here needs to be a potential divider, so it needs to be two resistors in series. Now that tells us there should be 20 volts going into the circuit from the supply. It then needs to be split equally between two outputs, so they must have the same resistance, because that will allow the potential difference to be shared equally. So each one will receive 10 volts. In this next one, we need to work out our output voltages. So V out is equal to R2 over R1 plus R2 times by V in. So it's 90 over 90 plus 270 times by 12 is 3 volts. And on this side, it's going to be 120 over 30 plus 120 times by 60 is 48 volts. In our next question, to assess your understanding, with examples, outline why it's necessary for different power sources to have different internal resistances. Describe what happens to the terminal PD from a power source as the current through the source increases. Then a 9-volt battery with an internal resistance of 2 ohms is connected in series with the filament lamp. The lamp draws a current of 1.5 amps. Calculate the loss volts, the terminal PD, the energy lost per second by the battery, and the resistance of the lamp. So pause the video now, then unpause the video when you want to go through your answer. So in this first one, a low internal resistance is needed to provide a large current in the circuit, for example in a car battery. A high internal resistance is needed to ensure a high current is not produced in the circuit, such as in a safety device. We know that as the current increases in a circuit, the terminal PD will decrease. We can work out loss volts as its current times by internal resistance, so it's 3 volts. Terminal PD is the EMF in minus the loss volts, so it's 9 minus 3, which is 6 volts. Energy loss per second is another word for power dissipated. Now we know from the electricity module, power dissipated is I squared R, where R is going to be the internal resistance because it's the power source, the battery. So it's going to be 1.5 squared times by 2, 4.5 watts. Resistance, we can use Ohm's law, R equals V over I. So it's 6 over 1.5, so it's 4 ohms. The next question says, to assess your understanding, two identical 1.5 volt cells, each with internal resistance of 0.75 ohms, are connected in series. So calculate the terminal PD when the cells supply a current of 0.80 amps to an external circuit, and then the cells are connected to a resistor of 10 ohms. Then repeat the calculations for the cells in A1, but they're now connected in parallel. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we know that EMF or PD is equal to the EMF minus the resistance. So we know our total EMF going in is going to be 1.5 plus 1.5, because when cells are in series, you add them. So therefore, we know that it's 3 volts. We know the total internal resistance, because there's 2 in series, so you add them, is 1.5 ohms. So we can work out our terminal PD, which is going to be 3 minus 0.8, the current, times by the internal resistance 1.5, so it's 1.8 volts. In the next one, we know that current is equal to EMF over the two resistances added up. So it's 3 over 11.5, our internal resistance plus our series resistance. Okay, so you can work that through to therefore be 0.26 amps. We know V equals PD is equal to the EMF minus the resistance, the loss volts. So you can work it through to be 2.6 volts. Now in this next one we will do the same, except this time we're working out our internal resistance. It's 1 over R equals 1 over R plus 1 over R. To work it through, you get it out to be 0.38 ohms. So you can tell our internal resistance in parallel is going to be less than it will be in series. The EMF stays the same. You work out the values, so it's 1.2 volts. And again, in this case, we can now work out our new total resistance with our new value for internal resistance. So you can work that through, and then you get an answer out to be 1.4 volts. Let's now have a look at some more assessment point challenging questions. So So the first question says, a smart greenhouse uses a potential divider to automatically control ventilation based on environmental conditions. In one part of a circuit, a 12-volt supply is connected across two components in series, a fixed resistor of 4.7 kiloohms and a thermistor whose resistance decreases as temperature increases. At a certain morning temperature, the thermistor has a resistance of 8 kiloohms. Later in the day, the greenhouse heats up and the thermistor resistance falls to 2 kiloohms. A microcontroller monitors the potential difference across the thermistor to decide when to activate a ventilation fan. Separately, another circuit uses a light-dependent resistor in a potential divider to adjust the shade of greenhouse automatically as the sunlight levels change. The resistance to the LDR is 10 kiloohms in bright sunlight and 20 kiloohms in cloudy conditions. Determine how the potential difference across a thermistor changes between morning and afternoon. Support your answer with calculations. Then in the LDR circuit, suggest how the microcontroller could use the changes in potential difference to determine whether the greenhouse is in bright or cloudy conditions. Explain your reasoning, including reference to how the potential difference across the LDR would vary with light intensity. Finally, evaluate the advantages and limitations of using thermistors and LDRs in a smart environmental control system. So pause the video now, then unpause the video when you want to go through your answer. So in this first question, we've got to use the potential divider equation in both times. So you can work it out in the morning. So when you work that then through, we're going to get our answer to be 7.56 volts. In the afternoon, when we work it through, we get 3.58 volts. So it tells us that the potential difference across the thermistor will decrease as the temperature rises. In our next question, in a potential divider, we know that the potential difference of the LDR depends on the resistance of the LDR relative to the other resistor. Now in bright light, the low resistance L will lead to a VLDR which will be small. In cloudy conditions with a high resistance, we know that the VLDR will be higher. So therefore the microcontroller can monitor the potential difference, the VLDR, okay, and a high potential difference will indicate a low light and a low potential difference will indicate a bright light. Now, we know that for this to work, simple, passive, cheap components will need no external power to function. Now, their resistance-environmental relationship can be nonlinear and can vary with component aging. So we know that it's suitable for simple control systems, but for precise applications, it will require calibration and adjustment for it to work. The next question says, a Mars rover uses a potential divider circuits to monitor critical environmental conditions. One potential divider circuit contains a fixed resistor of 5 kiloohms and an LDR whose resistance depends on the brightness of the sunlight reaching Mars' surface. The rover's control system is powered by a 9-volt supply. On a bright Martian day, the LDR's resistance is 3 kiloohms. In a dust storm, the LDR's resistance increases to 18 kiloohms due to the reduced light. Elsewhere on the rover, a second potential divider uses a thermistor to monitor internal equipment temperature. If the potential difference across the thermistor drops below a certain threshold, heaters automatically switch on to protect sensitive instruments. For the light sensor circuit, determine the potential difference across the LDR in both bright and dust storm conditions. Explain your reasoning clearly. Then describe how the thermistor circuit will behave as the rover's internal temperature drops during the cold Martian night. Refer to potential difference and the control of the heaters in your explanation. Then evaluate 2 advantages and 2 limitations of using LDRs and thermistors for automatic environmental control in space missions. So pause the video now, then unpause the video when you want to go through your answer. So in our first question, once again, we've got to use the potential divider equation. So in bright conditions, we can work it through to be 3.34 volts. In dusty conditions, we work it through to be 7.04 volts. So this tells us the LDR voltage or potential difference will increase in the dust storm as the light lowers. Now, in this next question, how would a thermistor work? Well, as the temperature falls, the NTC thermistor resistance increases. So the higher thermistor resistance shifts the potential divider output. So therefore the voltage across the thermistor will rise. The control system detects this and activates the heater to protect sensitive components. Now finally, again, it's simple, it's passive, it's reliable without moving parts, it's lightweight, it has a low power consumption, but the response may be nonlinear and may drift over time due to radiation damage from being in space or the material degrading over time. Now therefore it tells us it will be generally effective, but will require calibration for long missions and also be redundant for quite a bit of time. The next question says, during a race, a Formula 1 car uses a high power energy store or battery to supply extra energy during a pit lane exit boost. The battery has an EMF of 48 volts and internal resistance of 0.220 ohms. The electric motor it supplies has a load resistance of 4.8 ohms during normal operation. During a boost phase, the motor draws a much larger current, reducing its effective load resistance to 2 ohms. Calculate the current flowing through the motor during the normal operation. Then determine the terminal potential difference across the motor. Calculate the current and terminal potential difference during the boost phase. Comment on why the boost system designers must account for internal resistance carefully. Then evaluate the potential consequences for performance and battery management if the internal resistance was significantly higher than 0.20 ohms. So pause the video now, then unpause the video when you want to go through your answer. So, in this first one, what is the total resistance? Well, it's going to be the resistance of the circuit plus the internal resistance. So that's 4.8 plus 0.2 is 5 ohms. So the current is therefore the PD over the total resistance, so it's 9.6 amps. So the terminal potential difference is equal to the current times by the load resistance. So it comes to be 46.1 volts. In our next question, again, we know that the total resistance is going to be 2.2 ohms. We know that the current is therefore going to be PD over this, so it's 21.8 amps. So our terminal potential difference is going to be 43.6 volts. So what this tells us is something quite important, that the internal resistance causes a larger voltage drop at higher currents, so it reduces the effective voltage available to the circuit, the motor in this instance. So designers must minimize the internal resistance to maintain the motor performance when the high current is being drawn by the F1 car. Now finally, a higher internal resistance would cause larger voltage drops at high currents. This would reduce the terminal voltage significantly, cutting the motor power during this critical boost phase. Additionally, a higher internal resistance would cause more heating inside the battery of the Formula 1 car, risking thermal issues and shortening the life of the battery. The next question says, competitive esports tournaments sometimes requires players to bring their own portable power packs to ensure uninterrupted performance during outdoor or pop-up gaming events. An esports team uses a power pack with the following characteristics: an EMF of 15 volts, an internal resistance of 0.40 ohms. Their gaming laptop requires a stable input with a resistance equivalent to 12 ohms during normal operation. However, under intense gameplay and high processing load, the laptop's equivalent resistance drops to 6 ohms. The organisers have warned that if the terminal PD drops below 13 volts, the laptop's performance could suffer. So firstly, calculate the current drawn and the terminal potential difference across the laptop under normal operation. Determine whether the laptop would remain above the critical 13 volt limit during intense gameplay. Support your answers with appropriate calculations and reasoning, and then evaluate how important it is for esports players to consider internal resistance when selecting a portable power pack. Include 2 potential consequences of ignoring it. So pause the video now, then unpause the video when you want to go through your answer. Okay, in this first one, we've got to work out the total resistance. So it's 12, the load resistance, plus 0.40, the internal resistance. So it's 12.4 ohms. Current is PD over the total resistance, so it's 1.21 amps. The terminal PD or terminal voltage is equal to the current times by the load resistance, so it's 14.5 volts. Now, again, when you under this intense gameplay, our total resistance goes to 6.4 ohms, our current goes to 2.34 amps, and our terminal PD goes to 14.04 volts. So this tells us our terminal PD remains above 13 volts, so therefore the laptop performance would not suffer even during the intense gameplay. Now finally, high internal resistance can cause significant voltage drops under the load, risking poor device performance. The extra heat generated inside the battery can lead to safety risks or reduced battery lifespan. So you've got to select a power pack with low internal resistance to make sure it's for stability and it is safe to use. In the next question, in a future festival, students design autonomous robots powered by simple batteries and resistor circuits. One team builds a robot powered by the circuit shown below. The battery has an EMF of 12 volts and a negligible internal resistance. 2 resistors are placed in parallel. R1 is 4 ohms. R2 is 6 ohms. The resistor simulates different drive motors inside the robot. Calculate the total resistance of the circuit and the total current supplied by the battery. Determine the current through each resistor, and state and explain which branch will heat up more quickly if the resistors are not ideal and dissipate energy. Finally, the students wish to confirm Kirchhoff's laws practically using this circuit. Suggest one method they could use to verify Kirchhoff's first law at the junction and discuss a practical challenge they may face in doing so. So pause the video now, then unpause the video when you want to go through your answer. In the first question, they're in parallel. So 1 over R total equals 1 over R1 plus 1 over R2. So it's 1 over 4 plus 1 over 6. So R total is 2.4 ohms. Current is PD over the total resistance, so it is 5 amps. In each one, we know that the potential difference is going to be the same because they're in parallel. So each branch gets 12 volts. Now we know R1 is current is equal to PD over the total resistance of R1. So it's 12 over 4, it's 3 amps. Again in R2, it's 2 amps. This tells us the branch with R1, the lower resistance higher current, will dissipate more power and heats more quickly. Now the power dissipated, or P equals I squared R, is greater for higher currents because it's I squared even if the resistance is lower. Now finally, you could measure the current entering the junction and measure the current leaving the junction using two ammeters. So according to Kirchhoff's first law, the sum of the currents into the junction equals the sum of the currents out. Now the issue you have is, inserting an ammeter in the circuit will add an extra resistance, so will lead to a practical challenge there. Also, the connections will have to be firm to avoid any measurement errors. The next question says, a new deep sea research submarine is equipped with an experimental electrical distribution network. The submarine's onboard systems are powered by a 24-volt battery with an internal resistance of 0.50 ohms. The network divides power between two critical systems, the navigation system modelled by a 5 ohm resistor and a life support system modelled by an 8 ohm resistance. Now, both systems are connected in parallel to the battery. However, due to the harsh deep sea environment, all external wires introduce an additional resistance of 0.20 ohms each. Engineers need to check whether the systems will operate within safe voltage limits under full load. So apply Kirchhoff's second law to write the equation for a loop, including the internal resistance, the wire resistance, and one branch of the circuit. Now explain why applying Kirchhoff's second law is necessary when analysing circuits like this in engineering. Then calculate the current drawn from the battery. Hence determine the terminal potential difference across the battery and check whether each system receives sufficient voltage for correct operation. Assume each one requires at least 20 volts. So pause the video now, then unpause the video when you want to go through your answer. In this first question, the correct loop equation will be V equals I times by the internal resistance plus the current times by the internal resistance of the wire plus the current times by the resistance of the system itself. Now the internal resistance and wire resistance must be included because they're causing energy losses in the circuit, and Kirchhoff's second law is all about the conservation of energy around a loop, so it's necessary for predicting the voltage drops and the system performance when there's a current being drawn through it. Now in this next question, what should you do? Measure the current entering and leaving the junction using two ammeters. Then, according to Kirchhoff's first law, the sum of the current in was equal to the sum of the current out of the junction. And as we said before, an ammeter insertion may introduce extra resistance. The connections need to be firm to avoid measurement errors. The next question says, an autonomous delivery drone uses an onboard battery pack to power both its main motors and its navigation system. The drone's battery has an EMF of 24 volts. An internal resistance of 0.60 ohms. Now the drone's main motors are connected via a simple circuit. A potential divider is used to split the supply between the motors and a sensitive navigation module. The potential divider consists of two resistors, R1 which is 3 ohms and R2 which is 1 ohm. The motors require at least 15 volts across them for safe operation. The system draws a total current of 8 amps from the battery during the flight. Calculate the terminal PD across the battery during the flight. Determine the potential difference across R2. Determine whether the motors are operating safely and explain your reasoning. Now the engineer is considering replacing the potential divider with a system using electronic voltage regulators instead. Evaluate one advantage and one disadvantage of using a passive potential divider like this one compared to active voltage regulation for a drone application. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the internal voltage loss or loss volts is V equals I times by the internal resistance. So you work it through to be 4.8 volts. Terminal PD is the EMF minus the loss volts, so it's 19.2 volts. Our potential difference across R2, well, we know that we can work it through by looking at the resistance, okay, by V equals IR. So you can work through what our terminal PD is going to be, and you get it out to be 4.8 volts. Now in our next question, what's happening? Well, the motors will only receive 4.8 volts based on the potential divider setup. Now the required minimum for the motors to work is 15 volts, so therefore the motors will not operate safely and the potential divider's design is not appropriate, it's inadequate. Finally, a passive potential divider is simple, it's lightweight, requires no extra control electronics. However, the output voltage will vary with the load current, making it unsuitable for a stable critical system like a drone motor. Now, active regulation will provide a stable voltage regardless of the load variation, but it does add mass, it does add complexity, it will consume extra amounts of powers, which is a significant concern for a drone. The next question says, an elite cycling track uses an electronic timing system powered by a 9-volt battery. The battery has an internal resistance of 0.30 ohms. The system includes a light gate sensor requiring a stable 6-volt supply, a digital timer with a resistance equivalent to 12 ohms. A potential divider is used to provide a reduced voltage to the light gate. A potential divider consists of two resistors R1 and R2 connected in series across the battery. The light gate is connected across R2. So the total resistance of the potential divider is 15 ohms. Calculate the required value of R2 to ensure the light gate receives exactly 6 volts when connected. During the operation, the total current drawn from the battery is measured as 0.50 amps. Determine the terminal PD across the battery and explain how internal resistance affects the voltage supplied to the light gate and timer. Now, the race organisers are concerned that in longer events, battery performance could degrade further. Evaluate how a significant increase in internal resistance could impact the accuracy of race timing and suggest a suitable solution. So pause the video now, then unpause the video when you want to go through your answer. Okay. In this first one, we've got to use the potential divider equation to then work through all our values. But we're going to have to rearrange it to make R2 the subject when you work it all through. So when you pop in all the values, you get R2 to be 10 ohms. Now if you know the total resistance is 15 and R2 is 10, well therefore R1 is going to be 5. Now, in this next question, the internal voltage loss is going to be equal to I times by the internal resistance, so it's 0.15 volts. So therefore, the terminal PD is EMF minus the loss volts, 8.85 volts. Now, the slightly reduced battery voltage means the voltage across the potential divider will drop, leading to the light gate receiving less than the designed 6 volts it needs, which could possibly lead to an unreliable time and measurement. Now, an increase in internal resistance would cause a greater voltage drop, especially at the higher currents. So this could lead to an underpowered light gate and an inaccurate or missed race timings. So they need to implement a regulated power supply or capacitor to stabilise the voltage for critical sensors. Or they could replace batteries more frequently or design a system that allows you to tolerate small changes in the voltage of the circuit. The next question says, a battery of EMF 9 volts and internal resistance R is connected to two resistors P and Q as shown in figure 6.2. A total charge of 650 coulombs through resistor P in a time interval of 540 seconds. During this time, resistor P dissipates 4,800 joules of energy. The current in resistor Q is 4.5 amps. Assume the EMF of the battery remains constant. Calculate the current in resistor P, the potential difference across resistor P, and the internal resistance of the battery. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we know that current is equal to charge over time, 650 over 540, 1.2 amps. Now we know potential difference is the work done over the charge. Work done, 4,800 joules, divided by the charge, current times by time, so you work it through to be 7.4 volts. Finally, The internal resistance, well, we know that the current is going to be 5.7 amps because we have 4.5 amps, as is mentioned previously in resistor Q. We know in the other resistor it's 1.2 and they're in parallel, so then they'll add together, so you get 5.7 amps. We therefore know that we can work out the value because we know EMF is equal to the current times by the external resistance plus the internal resistance. So you pop in all the values, you get 0.28 ohms. Our next question says, a lamp is connected to a battery containing 2 cells as shown. The EMF of each cell is 1.5 volts and the internal resistance of each cell is 2.7 ohms. The reading on the ammeter is 64 milliamps. State what is meant by the EMF of 1.5 volts. Show that the lost volts in the battery is 0.35 volts. Determine the reading on the voltmeter. Calculate the power dissipated by the lamp, and in a different circuit an LED is connected to a battery containing 4 cells. The potential difference across the LED is 3.6 volts when the current through it is 26 milliamps. Determine the resistance of resistor R. So pause the video now, then unpause the video when you want to go through your answer. Now learn the definition of EMF. So that's 1.5 joules of energy is supplied to the circuit or gained by each coulomb of charge passing through the cell. Lost volts is current times by internal resistance. Pop in all the values, remember milliamps goes to amps, so it becomes 0.35 volts. So therefore, when we know that the idea that the potential difference will work through is add another one of the two values, we know our read on the voltmeter is going to be 2.7 volts. The power is equal to IV, so it's current times by potential difference, so it's 0.17 watts. Here we know that our terminal PD is equal to the EMF minus the lost volts. Work it all through and we get 5.7192 volts. Resistance is equal to PD over current. Now we need to work out the PD of the actual resistor because we're working out the resistance of the resistor. So that's the difference in the two values. We then divide it by the current, which is 26 times 10 to the minus 3, so we get 82 ohms. The next question says, Figure 10 shows the circuit diagram for a battery-powered torch. The circuit contains 3 identical light-emitting diodes and a resistor R. The current in the circuit is 44 milliamps. The battery has an EMF of 12 volts and an internal resistance of 1.5 ohms. Determine the resistance of R in Figure 10. Then another appliance is connected to a battery as shown in Figure 12. The current in the battery is 3.5 amps when the switch S is closed. Each LED requires a voltage of at least 2.9 volts to light. Deduce whether the LEDs will light when the switch is closed. So pause the video now, then unpause the video when you want to go through your answer. Okay, in this first one, we know V is equal to IR. So we pop in our values for I, which we know to be 44 times 10 to the minus 3 milli into amps, times it by R, which we know to be 1.5 ohms because we got our internal resistance there. So it's 0.066 volts. Now our total resistance minus our internal resistance is going to equal our resistance of the load or the circuit. So when you pop that through, we get 271.2 ohms. Now the total resistance of the 3 LEDs, we know each one is 77. They're in series and they're added together. So therefore it's 231.9 ohms. So therefore our resistance is going to be the difference, as we said, between the two values. So therefore it's going to be 39.3 ohms. Now, in this next question, we know that lost volts is going to be equal to current times by the internal resistance. So we work it through to be 5.25 volts. We therefore know our terminal PD is our EMF minus the lost volts, so it's 6.75 volts. Now, the LED won't light because the terminal PD is therefore less than 8.7 volts. Now, because the PD across the LED is less than 2.5, therefore there'll be no current in the LEDs because the potential difference across the resistor is 0, as the resistance of the LED is much greater than that of the resistor. So therefore there's no current in the LEDs. Now, the total PD required will be 9.01 volts, which is greater than the terminal PD. So it will not work. Our next question says, a technician sets up a circuit as shown, using a car battery and 2 identical lamps. The battery has an EMF of 12.8 volts and an internal resistance of 0.10 ohms. Switch S is open. The read on the ammeter is 1.80 amps. Determine the reading on the voltmeter. Now switch S is now closed. State the effect that this has on the reading on the voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Now in this first one, we know that V is equal to IR. Now we need to work out what the total resistance of the circuit is going to be. So it's going to be 4.8 of the resistor plus 0.1 of the internal resistance. So therefore we do V equals IR. We know the current is going to be 1.8 amps from the information in the question, it's 8.82 volts. So therefore the reading on the voltmeter will be the difference, because whilst we know that V is 8.82 in that particular part of the circuit, we also know that the EMF there coming into the circuit is 12.8 volts. So therefore the difference must be the voltmeter reading, which is 4 volts. Now, what happens if the switch is now closed? Well, with the switch is now closed, so we've added a bulb in parallel. So that tells us that our total resistance has decreased because our potential difference across the lamp has decreased. Now, it means that the lost volts, will therefore increase because the current going through the circuit, and it's a series circuit, so it'll be the same everywhere, has gone up because the resistance in the externals or the load circuit has gone down. So therefore, our lost volts will go up. Now the next question says, a battery has an EMF of 12 volts and an internal resistance of 0.50 ohms. The battery is connected into a circuit as shown. Each bulb has a normal working power of 40 watts when a potential difference of 12 volts is applied. Initially the switch is open. Calculate the terminal PD of the battery when bulb 1 is lit. Assume that the resistance of the bulb has its normal working value. Then explain how the brightness of bulb 1 changes when the switch is closed. No further calculations are necessary. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that power is equal to potential difference squared over resistance. We know the potential difference is 12, so therefore R is equal to 12 squared over 40 watts, so it's 3.6 ohms. Now we know current is potential difference over resistance. We know the EMF, or PD, because it's the same in this case, is 12 volts. We then divide it by the total resistance, which is the internal plus the circuit resistance, so it's 3.6 plus 0.5, so we get out our answer to be 2.93 amps. V equals IR. We've got R in the circuit to be 3.6 ohms. The current, which is the same throughout the circuit, is 2.93 amps, so it's 10.5 volts. Now, what would happen if the switch was closed? Well, as the switch closes, as we've mentioned before, the terminal PD will decrease because if you look through, the resistance of the circuit has gone down because there's now a device going through, if you look through into the question, in parallel. So therefore the resistance has gone down in total, so therefore the current has gone up. So that means the terminal PD will decrease, so the brightness of bulb 1 will therefore decrease. So that brings an end to this revision session today. If we've been successful and we've learned in today's lesson, we should be able to answer A-level physics examination style questions. You should be able to assess your understanding on A-level physics and finally understand what topics you need to improve upon for A-level physics. So thank you so much for watching this revision session on AQA A-Level Physics in the topic of electricity, looking at questions based on potential dividers and internal resistance. Thank you so much for watching and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of electricity. So in today's lesson we're going to look at how to answer examination questions for A-Level Physics Paper 1 on AQA on the electricity module. So if we've been successful and we've learned in today's lesson, we can answer A-Level Physics examination style questions on electricity, assess our understanding on A-Level electricity, and then understand what topics of the A-Level Physics module of electricity that we need to improve upon. So how should we prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this section, write down your working out or your answers to the questions in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst on the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? So the first thing you should be doing is learning the key facts. So using revision guides, class workbooks, student prep notes and the textbook to learn the key ideas of the course. You may wish to make a mind map or write out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca, a student knowledge checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then finally, you would practice examination questions. So use exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and mark your own work, and you may wish to download your own examination past papers to do this. So the 3 steps are to learn the key facts, then to test yourself, and then to practice examination style questions. So what questions will we be covering in this revision session? Well, we'll have 3 types of questions. The first one are your general checker questions, the basic questions designed to probe your understanding of the key concepts of the topic. The second one are the checkpoint questions, the more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally, we've got the assessment point questions, which are past paper exam questions which will mimic the type of questions found in public examinations. So let's start with this topic of electricity. So the first question says, describe the difference between resistance and resistivity. Calculate the resistance of a copper wire of length 1 meter in cross-sectional area 3.32 times 10 to the minus 6 meters squared. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Then explain the effect of changing the temperature on the resistivity of a metal, and calculate the resistivity of a piece of wire which has a resistance of 170 ohms when it has a length of 12 meters and a radius of 3 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, the main difference is that resistance will apply to a particular component. It depends on the component's dimensions, whilst resistivity is a property of the material itself. The material will have a constant resistivity at the same temperature. Now, to work out the second question, you say resistance is resistivity times by length over area. The equation is given to you on the equation sheet. Pop in all the numbers and you get 5.1 ohms. The next one, we know that temperature affects resistivity. So when the temperature of the metal increases, the positive ions of the metal have more energy. This makes the positive ions themselves vibrate with a greater amplitude, which will increase the number of collisions between the charge carriers and the ions every second, so therefore it increases the resistivity. Now in the last question, it's the same equation as before. We've rearranged it to make resistivity the subject, but this time we need to work out area. So you're given the radius, we assume that it's got a circular area, so it's pi r squared. We convert our millimeters into meters, and we pop in all the values and we get 4.0 times 10 to the minus 4 ohm meters. The next question says, what is the resistance of a sample of copper 2 meters long with a 0.50 millimeter squared cross-sectional area? The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Calculate the resistivity of a metal wire with resistance 2.5 ohms, length 1.8 meters and diameter 0.40 millimeters. Calculate the resistance of a copper rod of length 80 centimeters and diameter 0.5 millimeters. Then determine the length of nichrome wire of cross-sectional area 2.0 times 10 to the minus 7 meters squared required to make a 10 ohm resistor. The resistivity of the nichrome is 1.1 times 10 to the minus 6 ohm meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the resistivity equation. So resistance is rho L over A, but the trick is we're converting from millimeters squared into meters squared. So it's 10 to the minus 6 because there's 2 lots of 10 to the minus 3s going from millimeters squared to meters squared. So we get 0.068 ohms. The next question is we're working out the area again, but remember we're given the diameter, so we half that to find the radius, and we convert those millimeters into meters to work out our area. We pop into the equation and we get 1.74 times 10 to the minus 7 ohm meters. In question 3, again, it's the same idea. Remember, we're given the resistivity of copper earlier, and the resistivity of a material is constant. So therefore, we can say area is pi r squared. We can then pop it into the equation r equals rho L over A, and we get 0.069 ohms. And in this last one, we're rearranging. So now we're making L the subject. So L equals RA over rho. Pop in all the values and we get 1.81 meters. The next question says, sketch a graph of I against V for a metallic conductor at a constant temperature and use it to describe Ohm's law. The current in a resistor is 0.50 amps and as PD across it is 5.2 volts. Calculate its resistance. Then define the ohm and express it in base units. Then a length of wire is connected to a cell. The current in the wire is 80 milliamps and the PD across the wire is 2.4 volts. Calculate the resistance of the wire. Then a resistor has a resistance of 1.2 kilo ohms. In 3.0 minutes, a charge of 54 coulombs flows through the resistor. Calculate the PD across the resistor. Then the current in a filament lamp is 1.5 amps. It is operated for a time of 1 minute. The charges flowing through the lamp transfer 500 joules of energy to the lamp. Calculate the resistance of the lamp. So pause the video now, then unpause the video when you want to go through the answer. Right, so in this first one, the graph of I against V should be a straight line through the origin, because Ohm's law states that potential difference is directly proportional to current for a conductor at a constant temperature. Resistance is given to you as PD over current, so it's 5.2 over 0.50 is 10 ohms. Now we can use this to define the ohm. So the ohm is defined as the resistance that a component would have when a potential difference of 1 volt is produced per 1 amp of current. Now you can see that from the equation R equals V over I, 111 there. Again, to work out the value in base units, you've got to work that through, but 1 ohm is 1 kilogram meters squared seconds to the minus 3 amps to the minus 2. The next question will use that resistance equation again, but remember we turn milliamps into amps, so that's times by 10 to the minus 3. In the next question we can work out V by doing V equals IR, but we've got to firstly work out what I is. So I is Q over T. Again, all these equations are given to you on the equation sheet. So it's 54 over 180, because we don't work in minutes in physics, we work in seconds. So it's 0.30 amps. Pop it in there. Remember, kilo ohms turned into ohms by times it by 1,000. So it's 360 volts. And in this last one again, it's a multiple step calculation. We know that potential difference is work done over charge, which is current times by time. Pop in all the values. Again, we don't work in minutes, we work in seconds. So we get 5.55 volts. We say R equals V over I, so we get 3.7 ohms. The next question says, fill in the missing values for current in the electrical circuits. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that the current through a junction, what was going into the junction must come out of the junction. So the first one is 2 amps. The second one is 2 amps again, because it's all in one series circuit. Now for C, you'll notice it goes 3.2 at the junction. One of them coming out is 2.6, so what goes in must come out. So on the other side it must be 0.6 amps. Then they join again at the other side on that junction, so it comes out to be 3.2 again. And in here we've got it coming into the junction of 1.8 amps. On one side of the junction 0.6 amps is going out, so on the other side 1.2 amps must be going out as well. They rejoin up again at the next junction to give you 1.8 amps. The next question says, fill in the missing values for the potential difference in the following electrical circuits. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've got to remember that the EMF in equals the PD out for each branch, and each branch will have the same overall PD out. So we know in the first one 10 volts is going in, so 10 volts is going out, so the one must be 4 volts. In the second one we know 6 and 6 volts are going in, so that's 12 volts, so it must be for B 12 volts in total, because that's the only thing on that branch. But in the other one C must be 9, because 9 plus 3 equals 12. Now in D we know that 12 is going in, but we know that in parallel branches have the same potential difference. So for E it's in parallel with 4 volts, so it will have 4 volts, so therefore D will have 8 volts, like so. And in this one we've got to be very careful, because even though it's on the same line, it's on the same level as the two EMF sources, there's actually a 3 volt resistor there, so it's not producing EMF, it is in fact using up a potential difference. So the total input is 3 plus 9 volts, which is 12. So therefore we know that F must be 4 volts, because we know there's 6 volts below it, and on parallel branches you get the same EMF in total. So 2 plus 4 equals 6, so you got 6 from there, you got 3 from the other resistor, so therefore you must get 3 as well. The next question again says, fill in the missing values for potential difference in these electrical circuits. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we know EMF in equals PD out. So in this first one, we know it's 2.2 volts in, so the total must be 2.2 volts out, so that one must be 0.8 volts. Again, in B, we know that in total, we are going to have 8.7 out, so therefore we must have 8.7 in, so it's 3.7 there. Now in this next one, you've got to be very careful, because when you look at the orientation of the two cells, they're in opposite directions to each other. So we will consider one, most likely be 2.4 in this instance, to be a negative, because the EMF sources are acting in opposite directions. So therefore the total going in is not 8.4, rather it's actually going to be 3.6. So therefore the other one is 2.2 volts. And in this one, we know the total PD on that middle branch there, so we know it will be 9 volts, so it's 9 volts on the top one and 9 volts on the bottom. The next question says a 270 ohm resistor and a 170 ohm resistor are connected as part of a potential divider circuit to a 36 volt supply. The output is connected across the 270 ohm resistor. Calculate the output voltage, then outline how a pair of identical resistors can be used in a potential divider to produce an output of 10 volts from a 20 volt supply. Include a diagram in your answer. And then calculate the output voltage from the two potential dividers below. So pause the video now, then unpause the video when you want to go through your answer. Right, so we need to use our potential divider equation, which is V out equals V in times by the resistor which is being looked at divided by the total resistance, or you could say V is directly proportional to R. So in this instance, we say V out equals V in times by R2 over the total resistance. So the resistance resistor which we're measuring across is the 270 ohm. So it's 270 over the combined total of the two of them times by the input, which is 36. So we get 22 volts. Now a potential divider is fundamentally two resistors in series. Now to note, both resistors are equal, so therefore it'll split the potential difference equally because V is directly proportional to R. So you've got 20 volts going in, you've got 0 volts going out, and therefore each resistor has 10 volts going across from it being dissipated through it. This next one, we again use the potential divider equation. Remember, it is the wanted component's resistance over the total resistance times by the input. So we get 3 volts there, and we get 48 volts there. The next question says, with examples, outline why it's necessary for different power sources to have different internal resistances. Describe what happens to the terminal PD from a power source as the current through the source increases. Then a 9 volt battery with an internal resistance of 2 ohms is connected in series with the filament lamp. The lamp draws a current of 1.5 amps. Calculate firstly the lost volts, then the terminal PD, then the energy lost per second by the battery, and then the resistance of the lamp. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand that the internal resistance will limit the current in the circuit because it's a series circuit, so therefore the current in both the internal and the external circuit will be the same. So therefore, if you have a low internal resistance, you will therefore have a high current in the circuit, and a high internal resistance will give you a low current in the circuit. Now we know that terminal PD is equal to EMF minus lost volts. EMF stays fixed, but the lost volts can be calculated by the current times by the internal resistance. So as the internal resistance is a fixed value, when current increases, the lost volts will increase, so therefore the terminal PD will decrease because there's a greater proportion of the EMF being lost as those lost volts. Now you can work out lost volts, like we said, by doing internal resistance times by current. You've got each of those in that example, so the answer is 3 volts. Terminal PD is EMF minus lost volts, so it's 9 volts minus 3 volts, so it's 6 volts. Energy lost per second is another name for power dissipated. We know that power equals I squared R. That again is an equation given to us on the equation sheet. We know the current in the battery because it's constant throughout the circuit, 1.5 amps. We know the resistance of the battery because that is what internal resistance is, the resistance of the power source. So it's 1.5 squared times by 2 is 4.5 watts. Then we know what for the lamp, we know what the current is. It's in series, so it's always the same. It's 1.5 amps. We know its potential difference because that is the terminal PD, because it's the only output to the terminal PD. So we get our answer to be 4 ohms. The next question says, a piece of silicon has a length of 3 millimeters, a cross-sectional area of 6 millimeters squared, and a resistance of 200 ohms. Calculate the resistivity of silicon. Then a tungsten wire has a length of 14.1 centimeters and a radius of 2.34 millimeters. Tungsten has a resistivity of 5.6 times 10 to the minus 8 ohm meters. Calculate the resistance of this tungsten wire. Then, a scientist is designing a circuit and needs a copper wire 1 centimeter long with a resistance of 0.000547 ohms. The resistivity of copper is 1.68 times 10 to the minus 8 ohm meters. Calculate the radius the copper wire needs to be. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the resistivity equation. Remember, length goes from millimeters into meters. We know that millimeters squared goes into meters squared by doing times 10 to the minus 6. We work it through and we get 0.4 ohm meters. The next one again, we work out our area. We've got the radius, we convert that into meters. We then do pi r squared to then work out the area. We then say resistance is rho L over A. Pop in all the values. Remember, 14 centimeters turns into meters. So we get 4.6 times 10 to the minus 4 ohms. Then in this final one, we make area the subject in the resistivity equation. So we will convert centimeters into meters and we pop in the values for the area to get 3.7 times 10 to the minus 7 meters squared. We then say the radius is the square root of the area over pi, rearranging the equation for a circle's area, and therefore we get 3.42 times 10 to the minus 4 meters. The next question says, there is a current of 10 amps through a lamp for 1 hour. Calculate how much charge flows through the lamp in this time. Then calculate the current in a circuit when a charge of 180 coulombs passes a point in the circuit in 2 minutes. Calculate the number of protons which would have a charge of 1 coulomb. In which of the following quantities of electrical charge is possible, and explain how you know this. 6 times 10 to the minus 19 coulombs, 8 times 10 to the minus 19 coulombs, and 10 times 10 to the minus 19 coulombs. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out what the time is going to be, but we convert the time from hours into seconds. So it's 3,600 seconds. Charge equals current times by time. We've got the current, we've got the time, so we get 3.6 times 10 to the 4 coulombs. This next one, we know that current is charge over time. Pop in all the values. We don't use minutes, we use seconds in physics. So we get 1.5 amps. Now, how many protons would have a charge of 1 coulomb? So you do the number of protons in 1 coulomb is the charge in coulombs divided by the charge of 1 proton, or electron in this instance. So it's 1.6 times 10 to the minus 19, so that's 6.2 times 10 to the 18 protons. Now the only one which is possible is 8 times 10 to the minus 19. That's because we know that the fundamental unit of charge comes in multiples of 1.6 times 10 to the minus 19 coulombs. That is a fact in physics. So you can only find one which is a multiple of 1.6 times 10 to the minus 19, which is 8 times 10 to the minus 19 coulombs. The next question says, figure 11.14 shows a piece of silicon of width 32 millimeters and length 36 millimeters. The resistance of the silicon between points P and Q is 1.1 mega ohms. Silicon has a resistivity of 2.3 times 10 to the 3 ohm meters. Firstly, calculate the thickness of the piece of silicon. Calculate the current that will pass through the silicon if a potential difference of 12 volts were applied across P and Q, and then discuss how the current would change if it was large enough to cause the silicon to become significantly warmer. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you've got to use the resistivity equation. So you say R equals rho L over A, but also area is thickness times by width. So you can work out the thickness by doing the area by working that value out, and then saying that the thickness is going to be the area over the width. So you pop in all the values. Remember, those width and length values need to turn from millimeters into meters. Be careful on that. So we get 0.024 meters. The next one, in terms of the current, well, current equals potential difference over resistance. We're given the potential difference in the question, and we know what the current is when you're working it through, the resistance, because you're given the previous question, so it's 1.1 times 10 to the 6. So the answer is therefore 1.1 times 10 to the minus 5 amps. This next one, we've got to think about what would happen in this instance. Well, in this instance, the resistance would decrease and the current would increase because the silicon, you've got to be aware, is a semiconductor. So in a semiconductor, when you increase the temperature, it releases more charge carriers into the circuit. That decreases the resistance and increases the current. The next question says, explain why the resistance of a metal increases when its temperature increases. State two of the factors which determine the resistance of a stated length of wire. Then when a potential difference of 1.5 volts is applied across a 5.0 meter length of insulated copper wire, a current of 0.24 amps is measured in it. Firstly, calculate the resistance of the length of wire. Then the resistivity of copper is 1.69 times 10 to the minus 8 ohm meters. Calculate the diameter of the wire. Then the wire is now made into a tight bundle. State and explain how you'd expect the current in it to change. So pause the video now, then unpause the video when you want to go through your answers. Right, you've got to understand how resistance and resistivity is affected by the temperature for a conductor. So as we said before, when the temperature increases, the atoms vibrate with a greater amplitude, so therefore there are more collisions per second. That increases the resistance. Now the other factors that affect resistance include the cross-sectional area, the length and the material of the wire. In this next one, how do you work out resistance? Well, it's V over I. You've got V, you've got I, so it's 6.25 ohms. This next one, we use the resistivity equation and we work out the area. So you work out your area to be 1.35 times 10 to the minus 8 meters squared. You can then say diameter is the square root of 4 times the area over pi. Okay, and then you can work it through to be 1.3 times 10 to the minus 4 meters. And in this last one, we notice that what happened to the current in it? Well, if you've got in a tighter bundle, there's less area to the open air, so they're less likely to dissipate energy out to the surroundings, so there's less cooling, the temperature rises, therefore the resistance will increase for the reason stated previously, so the current will go down. The next question says, a filament lamp and a 220 ohm resistor are connected in series to a battery of 6.0 volts EMF. The battery has a negligible internal resistance. A high resistance voltmeter is placed across the resistor and measures 1.8 volts. Calculate the current drawn from the battery, the PD across the lamp, the total resistance of the circuit, and the number of electrons passing through the battery in a time of 1 minute. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we know that current is going to be equal to V over R. We've got V for the resistor, okay, and then you can work out what R is going to be. So it's going to be 220 ohms. So therefore, it's going to be 1.8 over 220, which is 8.2 milliamps. Now, whilst you might think, yes, that's the current in the resistor, but it's also the current in the battery because they're in a series circuit and the current is constant throughout. Always look to what you can work out for particular components. The potential difference across the lamp is going to be 4.2 volts because the total EMF from the battery is 6. The voltmeter takes 1.8, so the lamp must be taking 4.2. Now the total resistance in the circuit must therefore be the total EMF divided by the total current, so you can work it through to be 6 over 8.2 times 10 to the minus 3 milliamps into amps, so you get 730 ohms. Now, how can we work out the number of electrons passing through? So you work out the charge. You know from the equation sheet, charge equals current times by time. Now, 1 minute we convert to 60 seconds, so we get 0.492 coulombs. So therefore, to work out the number of electrons, you work out the total charge divided by the charge on one electron, so you get 3.1 times 10 to the 18 electrons. The next question says, explain what is meant by the internal resistance of a cell. When a cell is connected in series with a resistor of 2.00 ohms, there is a current of 0.625 amps. If a second resistor of 2.00 ohms is put in series with the first, the current falls to 0.341 amps. Calculate firstly the internal resistance of the cell, then the EMF of the cell, and then a car battery needs to supply a current of 200 amps to turn over the starter motor. Explain why a battery made of a series of cells would not be suitable for a car battery. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, what's the definition of internal resistance? It's the resistance done to the work in driving the current through the EMF source or through the cell. Okay, now in terms of the internal resistance, we know from our equation sheet EMF is equal to current times by the external resistance plus the internal resistance. We can see the external resistance is 2 ohms from the information given. That's the resistance of the circuit in general. We've got the current, okay, so we know it to be 0.625 amps. Okay, we can see that we can link the two together by talking about if you put a second resistor in series, it's going to turn to 4 ohms, pop them through, work out R, it's 0.40 ohms. Therefore, we can use this equation to work out the EMF by saying EMF equals I big R plus small r. We know small r, we know big R, and we know current is a combination, so the EMF will equal 1.50 volts. Now, you'll notice that when you put cells in series, the resistance of each cell, the internal resistance, will add. So therefore, if you put them all in series, the internal resistance will get too high, so you wouldn't get a maximum current above 4 amps due to this internal resistance. The next question says, a circuit diagram shown below shows a 12 volt power supply connected to some resistors. The current in resistor X is 2.0 amps and the current in the 6 ohm resistor is 0.5 amps. Calculate firstly the current in resistor Y, then the resistance of resistor Y, then the resistance of resistor X. So pause the video now, then unpause the video when you want to go through your answer. Right, you'll notice by looking at the idea that if the current in X was 2.0 and the current in the resistor was 0.5 amps, well, the current going into a junction equals the current going out, so it's 1.5 amps. What's the resistance of Y? Well, we know the potential difference across Y is going to be the current times by the resistance. So we know the current is 0.5 amps, the resistance is 6, so the PD is 3 volts. So therefore the resistance across Y is going to be R equals V over I. We know V is 3, we know the current is 1.5 from the previous question, so therefore the resistance is 6 ohms. And then for X, we can say that the potential difference across X, because we know that the other one's taken 3, this must take 9, R equals V over I, it's 9 over 2, it's 4.5 ohms. The next question says, a student connects the circuit shown. The battery has a negligible internal resistance. The student increases the resistance of the variable resistor from 0 ohms to 40 ohms. Determine the range of readings on the voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Right, so this one is using the potential divider equation like we talked about before. Now, when the variable resistor is at 0, that is going to take 0 volts because V is directly proportional to R. So therefore, all the volts are going to go through the resistor and therefore the voltmeter because they're in parallel with each other. So we'll take them all from the battery, which is 6 volts. Now, to work out how much it would take when there's the maximum value for the variable resistor, well, we know that the resistor itself will have 10. The total in the circuit will be 50. So it's 10 over 50 times by 6, which is 1.2 volts. So there's the range of values your variable resistor would be measuring in the circuit. The next one says a battery of electromotive force 9 volts and negligible internal resistance is connected in series with an LDR and a fixed resistor of resistance 1800 ohms. A voltmeter is connected across the fixed resistor. The reading on the voltmeter is 5.4 volts. Calculate the current in the circuit. Then calculate the resistance RL of the LDR, and then the intensity of the light illumining the LDR increases. By reference to the current in this circuit, state and explain the change, if any, to the voltmeter reading. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you know the resistance of the resistor, you know the current going through, you know the potential difference going through the resistor because you know the value from the voltmeter. So you can work out the current for that resistor and it's going to be the same everywhere because it's a series circuit. Always look to see what combinations of values you have given in that circuit. So the current is going to be equal to V 5.4 over the resistance 1800, so you get 3.0 times 10 to the minus 3 amps. What's the resistance RL of the LDR? Well, you ratio the two of them because V is directly proportional to R. So if 1800 ohms takes 5.4 volts, what will 3.6 volts get you? Remember, because we know that if there's 9 in total and the other one takes 5.4, that one must take 3.6. So therefore we get our answer to be 1200 ohms. Now in this next one, you've got to be aware that when the light intensity increases on an LDR, that will decrease the resistance of an LDR. That's a fact you've got to learn. So if the total resistance of the circuit goes down because the LDR's resistance goes down and the other resistor is fixed, well, therefore the current will increase. So because there's a greater current going through the actual component, the potential difference will also increase, so therefore the voltmeter reading increases. The next question says, a single cell of EMF 15 volts is connected across a 0.30 ohm resistor. The current in the circuit is 2.5 amps. Calculate the terminal PD and explain why it's not equal to the EMF of the cell. Then show that the internal resistance of the cell is 0.30 ohms. It suggested that the power dissipated in the external resistor is a maximum when the resistance R is equal to the internal resistance of the cell. Calculate the power dissipated when R equals R. Then show that the power dissipated when big R is 0.50 ohms and small r is 0.20 ohms is less than that dissipated when R equals R, as the above statement suggests. So pause the video now, then unpause the video when you want to go through your answer. Right, so be aware that terminal PD is going to be equal to I times by the external resistance of the circuit. So in this case, it's 2.5 times by 0.30, 0.75, and therefore that's the work, and the terminal PD is not equal to the EMF because the terminal PD you got to subtract the lost volts due to the internal resistance from the EMF. Now in this next one, we know E equals the terminal PD, I times by big R, plus the internal resistance times by small r, the lost volts. Pop in all the values, work it through, and we get small r equals 0.30 ohms. Now in this next one, work out what the power dissipated will be. Well, P equals I squared R in this case, so it's 2.5 squared the current times by R, which is going to be the internal resistance because we're looking at the power dissipated in the cell. So therefore you work it through to be 1.88 watts. Now therefore you can work out the total power by working through again by I squared R, working the current when you got the total resistance in there to be 0.80 because we're adding the two because they equal each other. So therefore we get 1.76 watts. So why is it not the same? Well, you can work out the values there, work them out together, work it through, and you'll see that both is less than 1.88 watts, so therefore it can't be the case. The next question says, explain the difference between the terms EMF and potential difference. Then figure 10.28 shows a circuit containing batteries and resistors. You may assume that batteries have a negligible internal resistance. Firstly, use Kirchhoff's first law to find the current in the 4 ohm and the 8 ohm resistors. Then calculate the EMF of E1, then the value of E2, and then calculate the current in the 12 ohm resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, as we said before, the potential difference across the terminals of a battery, the terminal PD, is the work done per coulomb of charge in the external circuit, whilst the EMF is the theoretical work done per coulomb charge that goes into the circuit. Now in this next one, if we look it through using Kirchhoff's law, it's 0.75 amps, and then the EMF of this circuit, V equals IR. So we've got I, 0.75 amps, we've got the external circuit resistance, 12 ohms, so you can work it through to be 9 volts. Here again, use the circuit loop ideas with the batteries in both of them and the 3 ohm resistor. Again, total EMF in equals PD out. So the EMF of that particular component is 6 volts. So therefore the current is therefore I equals V over R. It's 6 over 12. It's 0.5 amps. The next question says, a nichrome wire has a length of 1.5 meters and a cross-sectional area of 0.080 millimeters squared. The resistivity of nichrome is 1.3 times 10 to the minus 8 ohm meters. Calculate the resistance of the wire, and then calculate the length of this wire which we needed to make an element of an electrical heater of resistance 30 ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you work out resistance? Well, we've got to use the equation, the resistivity equation. R equals rho L over A. Pop in all the numbers. Remember, we convert the millimeters squared into meters squared, 10 to the minus 6. We'll get the values through, and it's 0.24 ohms. Now, this next one, we need to change it and make L the subject. So L equals RA over rho. Again, resistivity will stay constant because it's the same material. Pop in all the values and we get 184 meters. The next question says, Figure 4 shows the IV characteristics of a slice of semiconductor material. Firstly, define resistance. Then show that the resistance of the slice is about 250 ohms when there's a current of 40 milliamps in it. Then the dimensions of the slice are shown below. Calculate the resistivity of the semiconductor material when there's a current of 40 milliamps in this slice. Then explain how the IV characteristic shows that the resistivity of the semiconductor material decreases with increasing temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, so defining resistance. So look at the equation to help define it. So we can say that that resistance is equal to the potential difference divided by the current. Now this next one, how do we show that the resistance is the case? Well, R equals V over I. Pop in all the values. Remember, 40 milliamps turns into amps, so therefore R equals 250 ohms. In the next question, work out the resistivity. Well, we know resistance is equal to rho L over A, so rho is equal to RA over L. Pop in all the values, work it through, and you get 0.30 ohm meters. Now in this last one, we know in the IV characteristic graph, okay, that when you got a semiconductor material, the graph will curve. So that indicates to you that the resistance of the material is changing. Now as it's curving, this tells you that the current is increasing faster than the potential difference is increasing. Now what's happening is the increased temperature is caused by the current. Okay, so therefore what you can therefore say is that as R decreases, because it's linked intrinsically to the resistivity will also decrease as well. The next question says, Figure 12.13 shows a potential divider. The battery has a negligible internal resistance and the voltmeter has an infinite resistance. State and explain how the read on the voltmeter will change when the resistance of the variable resistor is increased. Then resistor R2 has a resistance of 470 ohms. Calculate the value of the variable resistor when the read on the voltmeter is 2.0 volts. The voltmeter is now replaced with one of resistance 2 kilo ohms. Calculate the resistance on this voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what will happen is that you'll notice that as the variable resistor is increased, well, therefore, you can see that the current through R2 will decrease because you know that the resistance has gone up, so the current of the circuit will go down. Or you could say, well, when the resistance of the variable resistor goes up, the variable resistor will take more potential difference because V is directly proportional to R, so therefore the voltmeter, which is measuring the other device, will have less potential difference going through it, so its reading will decrease. This next one, we use the potential divider equation, pop in all the values, and we get 1600 ohms. Now this next one, the voltmeter has now got a resistance. It's now 2000 ohms. Now it's in parallel with another component. So we're going to have to use the parallel resistor equation to work out the total resistance of the resistor and the voltmeter. So it's 1 over 470 plus 1 over 2000, then 1 over that value, so you get 380 ohms. Now remember, when things go in parallel, the total resistance is always less than any of the individuals, so 380 ohms makes sense. We can then pop that into the potential divider equation. Remember, that's the wanted output, so it's 380 over the total times by the input, which is 9, which is 1.7 volts. The next question says, the photograph on the screen shows a statue of the Buddha in Sri Lanka, which is protected by a lightning conductor. During a storm, the potential difference of 2.7 megavolts was generated between a cloud and the top of the lightning conductor on the statue. A flash of lightning passed between the cloud and the lightning conductor, producing a current of 25 kiloamps for a time of 7.5 milliseconds. Calculate the energy transferred by the lightning strike. The lightning conductor is a length of copper wire with a diameter of 1.2 times 10 to the minus 2 meters and a resistance of 4.3 times 10 to the minus 3 ohms. It runs along the back of a statue from the base to a height of 1.5 meters above the top of the statue. A guidebook claims that the statue is over 30 meters high. Assess the validity of this claim. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Then give a reason why the lightning conductor should be taller than the statue. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out energy transferred. Now we know that energy transferred is the potential difference times by the charge. Now we can work out the charge by doing current times by time. Now we are given the time, okay, as 7.5 milliseconds. We convert that into seconds. We then convert our current of 25 kiloamps into amps by just times by 10 to the 3. So we get our charge out to be 188 coulombs. Then we can say work done is charge times by potential difference. Pop in all the values. Megavolts turns into volts by doing times 10 to the 6. So we get 5.08 times 10 to the 8 joules. In this next one, we need to work out the length of the wire. So therefore we use the equation R equals pi r squared, or pi d squared over 4. We work out the area of the wire. We then use the equation for length, so length is RA over rho. We get our answer out to be 28.6 meters. Now it's important to note it said in the question that the wire was 1.5 meters taller than the statue. So the statue's actual height is 1.5 meters minus that value, so it's 27.1 meters, so the claim is not correct. Now the lightning conductor should always be taller than the statue, so the lightning makes contact with the conductor rather than the statue. The next question says, resistivity paper is paper covered with a thin layer of carbon. The distance between the ends of a piece of resistivity paper is 12 centimeters, and the resistivity paper is 4.2 centimeters wide as shown. The resistance between the ends of the resistivity paper is 8.8 ohms. Calculate the thickness of the layer of carbon. The resistivity of carbon is 3.7 times 10 to the minus 5 ohm meters. A student connected the ends of the resistivity of the paper to a cell of EMF 1.5 volts, and the voltmeter is shown. The reading on the voltmeter was 1.4 volts. Calculate the internal resistance of the cell. Then the connection to the right hand terminal of the voltmeter was moved to a distance of 3.0 centimeters from the left hand side of the resistivity paper. Determine the reading on the voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out the resistance from this. So we use the resistance equation, R equals rho L over A. But the trick is now, area is going to be thickness times by width. So like we had before, we pop in all the values. We therefore say area is thickness times width. We convert all of our millimeters and centimeters into meters. So we then pop them through and we get the thickness to be 1.2 times 10 to the minus 5 meters. This next one, we can work out the current. Now remember, you can do it either with the external circuit or with the internal circuit. Now with the external circuit, we know that it's 1.4 volts, because it's running the voltmeter. We know what the resistance is externally. It's 8.8 ohms, it tells you earlier. So the current is 0.16 amps. Now because it's a series circuit, the current in the external circuit is the same as the internal circuit. So therefore, internal resistance is going to be equal to the value in the lost volts, which we know to be 0.1, because it has 1.5 EMF and then 1.4 terminal PD. So therefore the lost volts is 0.1, 0.1 over 0.16, it's 0.63 ohms. Now for this next one, we know that V is directly proportional to R, and R is directly proportional to length. So if you quarter the distance from 12 centimeters to 3 centimeters, you will quarter the length, you will quarter the resistance, you will quarter the potential difference. So the answer is 0.35 volts. The next question says, in the circuit shown, the battery has a negligible internal resistance. If the EMF is equal to 9 volts, R1 is 120 ohms and R2 is 60 ohms, calculate the current flowing in the circuit. Then calculate the voltage read on the voltmeter, and then the circuit shown in the diagram acts as a potential divider. The circuit is now modified by replacing R1 with a temperature sensor, whose resistance decreases as the temperature increases. Explain whether the read on the voltmeter will increase or decrease as the temperature increases from a low value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the equation EMF is equal to I times by R plus R, so you can work it through like so. So V equals IR, so therefore you can pop in all the values, work it through, work out the values there, and I equals 50 milliamps. Now this next one, the read on the voltmeter, well, V equals IR. We know the current because it's the same through both of them because it's a series circuit. So we know it's 80 milliamps or 0.05 amps. We know that R for this particular case is 60. So therefore V equals IR. So therefore it's 3 volts. Then this last one, we've got to be aware about how the temperature sensor works as the temperature increases. You've got to remember that as the temperature increases, the resistance of a thermistor, a temperature sensor, will always decrease. So therefore the total resistance of the circuit will decrease. That means the current through the circuit will increase because the total circuit resistance has gone down. So that will increase the voltage through R2 because you've got a greater current going through it. Or you could also say the reason is because if we know that in the temperature sensor, if R goes down, V goes down because they're directly proportional, so therefore the other device must have a greater value of V to satisfy Kirchhoff's laws, so therefore have a larger share of the 9 volts. So thank you very much for listening to this revision session on electricity for AQA A-Level Physics. If we've been successful and learned in today's lesson, we should be able to answer A-Level Physics examination style questions on electricity, assess our understanding on A-Level Physics for electricity, and then finally understand what topics we need to improve upon for AQA A-Level Physics on the idea of electricity. So thank you so much for listening to the revision session on electricity for AQA A-Level Physics Paper 1. Thank you so much and have a lovely day. Hello and welcome to this revision session for the electricity topic in AQA A-Level Physics. So in today's revision session we're going to look at how you answer examination questions for the A-Level Physics topic on paper 1, electricity. So if we are successful in this particular revision session, we'll be able to answer A-Level Physics examination questions on electricity, assess our understanding on this concept, and then understand what topics we need to improve upon for this particular topic of A-Level Physics. So how do you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the one on the right hand side, and in this left hand section write down your working out and your answers to the question in the revision session. Now when you're doing this, make sure you write your answers in full sentences and show your full working out for your calculations. Whilst on the right hand section of your paper, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of this revision session, write up these notes into a revision sheet for you to use independently. So before we begin on looking at questions on electricity, how can you revise this topic independently? So the first step you would need to be doing to revise this topic is learn the key facts. The first step is gaining knowledge. So use your revision guides, your class workbooks, your prep notes, your textbook to learn the key ideas of the course, and you might want to make mind maps or write out notes for yourself. The second step is to test yourself, to retrieve your knowledge and understanding. So you can use Caboodle, Seneca, a knowledge checker to quickly test your own knowledge, and you might wish to do this from your own cue cards. Then the third step is to practice examination style questions. So use exam prep books, homework books, supervised study books, additional workbooks to help answer exam questions and mark your own work. So you may wish to download your own examination papers to do this, and along with their mark schemes. So your 3 steps of learning the key facts, testing yourself and practicing examination style questions are key and crucial for revising this particular topic in A-Level Physics. So let's start off in this revision session by looking at some multiple choice questions. So the first question is, a 1.5 meter length of wire has a cross-sectional area of 5 times 10 to the minus 8 meters squared. When the potential difference across its ends is 0.20 volts, it carries a current of 0.40 amps. The resistivity of the material from which the wire is made is which answer? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer for this one is B. Now, the reason for this is we know resistivity is equal to the resistance times by the area over the length. Now, in this question, you aren't given the resistance, but you are given the current and the potential difference. Now, you've then got to remember that resistance is potential difference over current. So you've got that value for resistance. You can then multiply it by the area, which is given in the question. You then divide it by the length, which once again is given in the question. So you get an answer of 1.67 times 10 to the minus 8 ohm meters. Our next question says the resistance of a metallic conductor increases with temperature because at higher temperatures. So pause the video now, then unpause the video when you want to go through your answer. Right, the answer for this one is C, and this is a very important idea to understand. Now, when the temperature of any material increases, the ions that it's made from vibrate more, because temperature is a measure of the kinetic energy store of the particles in the substance. So if these ions, these particles, have more kinetic energy, they will vibrate more because it's a solid, so they can only vibrate, they can't move around. So this increases the chance of their collisions with our mobile charge carriers, the electrons, probably in this instance, so therefore it will increase the resistance. Our next question shows a graph of a current voltage characteristic of a filament lamp. So what is the resistance of the filament when the potential difference across it is 4 volts? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer for this one is A. Now hopefully you do remember that resistance is potential difference over current. So what you want to do is use your graph to then, when you've got 4 volts, you then find the current and then use the equation resistance is potential difference over current to find your answer. Now the important thing to note is on the y-axis the label says milliamps, not amps. So you've got to convert your value of current from milliamps into amps. Milli means times 10 to the minus 3 to work out your answer. Next question. The current in a wire is 40 milliamps. How many electrons pass a point in the wire in 3 minutes? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer for this one is B. Now we know the equation is charge is equal to current times by time. Now that's a very famous equation which you are given in your exam, but hopefully you can remember from GCSE physics. Now the important thing to note is in physics we don't use minutes, we use seconds. So we've got to convert our 3 minutes into 180 seconds. So we do our current, which is 40 milliamps, so the milli turns into just 10 to the minus 3, times by your time in seconds, gets you 7.2 coulombs for your charge. Now at this point you should hopefully remember that every electron has a charge of 1.6 times 10 to the minus 19 coulombs. So if the total charge is 7.2 coulombs, the charge of one electron is 1.6 times 10 to the minus 19 coulombs. Dividing one number by the other gives you the total number of electrons, which is 4.5 times 10 to the minus 19 electrons. The next question shows us a diagram of a resistor of resistance R across a cell of EMF E and an internal resistance little r. So which of the following is the correct expression for the current I? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer for this one is C. Now we know this because the equation given in the equation book in your examination is EMF is equal to I times by big R plus small r. So therefore we've got to rearrange it to make I the subject. So therefore I is equal to the EMF over big R plus small r, which is C. Our next question gives us a network of resistors, and the question asks us which of the networks has the largest total resistance. So pause the video now, then unpause the video when you want to go through your answer. Right, the answer for this one is C. Now why is the answer C? Well, you can work out each one individually, but remember when things are in parallel, the total resistance is 1 over R total is equal to 1 over R1 plus 1 over R2. So if you look at A, you can work out that our total resistance is going to be 1.3 ohms, because you can work out what it's going to be in the series, which is going to be 2 on the top and 4 on the bottom. So it's 1 over 2 plus 1 over 4, because then we flip it over to get 1.3 ohms. For B, we know it's going to be 1 over 3 plus 1 over 3, because the 1 plus 2 adds because they're in series. You can then flip it over, get 1.5 ohms. Now for C, you're going to do 1 over 1 plus 1 over 1 plus 1 over 2 there, to therefore give, and then flip that over to get you that total resistance in parallel. Then add 2 ohms because it's, add 2 ohms because it's in series, so it's 2.4 ohms. Then you do the same for D, which is 1 over 1 plus 1 over 2 plus 1 over 2. Then you flip it over, then add 1 because that 1 ohm resistor is in series, and you get 1.5 ohms. So the answer with the largest total resistance is going to be C, and it's hinted at in the question because you've got a 2 ohm resistor, the largest resistor in actual series, and resistors in series always add. Our next question shows us a potential divider circuit that contains a negative temperature coefficient thermistor, which is a normal thermistor. The temperature of the room containing the circuit increases. Select which row of the table correctly shows the changes in Vx, Vy and A. So pause the video now, then unpause the video when you want to go through your answer. Right, our answer for this is B, because as the temperature increases, the resistance across the thermistor decreases, because we should hopefully remember that it's a negative temperature coefficient. So therefore, when the temperature goes up, the resistance goes down. So therefore, that's going to cause the current to increase in the circuit, because A, there's more charge carriers released by the thermistor, and B, there's a lower resistance in the thermistor. So therefore, our current will increase, or our reading on our ammeter will go up. Secondly, the potential difference increases across the resistance because across the resistor, because as the total PD in equals the total EMF, so the total PD out equals the total EMF in. If our thermistor has a smaller resistance, it's going to be taking a smaller PD, so therefore the PD across the resistor is going to have to increase to compensate for that. So our answer is B. The next question shows a battery connected to a 10 ohm resistor and a switch in series. A voltmeter is connected across the battery. When the switch is open, the voltmeter reads 1.45 volts. When the switch is closed, the reading is 1.26 volts. What is our internal resistance of the battery? So pause the video now, then unpause the video when you want to go through your answer. The answer for this is D, because the EMF of a circuit is 1.45 volts. So when the circuit is off, you're going to have your total EMF, because that's what you're still putting into the circuit, so it'll be 1.45 volts. So the terminal PD of the circuit is 1.26 volts. So that's what's actually coming out when we've actually switched our circuit on. So therefore we must be losing in our circuit due to internal resistance 0.19 volts, because that's the difference between the two values. So we now know that current is equal to PD over load resistance. Now we know in the question it tells us our load resistance, our resistance of the circuit is 10 ohms. We know our PD is 1.26 volts because that's what's actually in the circuit. So our current is 0.126 amps. Internal resistance is lost volts over current. We know our lost volts will be 0.19 volts. Our current will be 0.126 amps. So therefore our internal resistance is 1.51 ohms. Our next question says a potential divider circuit consists of a battery connected across a thermistor and a variable resistor in series. Which of the following causes the PD across the thermistor to increase? So pause the video now, then unpause the video when you want to go through your answer. Well, our answer for this is D, because increasing the temperature of a thermistor decreases R in the thermistor, and therefore the PD across the thermistor will go down. Increasing the resistance of the resistor decreases R in total and the PD across the thermistor, because the resistor will take more of that PD from the battery, or from the from the battery, so the thermistor will have less. And finally, reducing the EMF will decrease the PD across both the thermistor and the variable resistor, because there's just less energy going into the circuit. So our answer would be D. Let's have a look at a few longer questions for electricity. So the first question says a cell has an EMF of 1.5 volts and an internal resistance of 0.65 ohms. State what's meant by an EMF of 1.5 volts. The current in the circuit is 0.13 amps, so that the total power output of the cell is approximately 0.47 watts, and then calculate the energy dissipated per second in the resistor R. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one's asking for the definition of EMF. So we know EMF is the work done per unit charge. So you would say in this context, because it's 1.5 volts, you would say you've got 1.5 joules of work is being done to move 1 coulomb of charge through the cell. Or you could say 1.5 joules of energy is converted to other forms for every 1 coulomb of charge. Now the next question is asking for us to work out the power. Now we hopefully should remember that power equals VI, a very important equation. We're already told in the previous question, if you look what V is, it's going to be 1.5. We know what the current is. It's given the question is 0.31. Multiply the two together to get your answer of 0.465 watts. And finally calculate the energy dissipated per second in the resistor. Now what you've got to understand is that the total power into a circuit equals the total power out. So if we know what the total power going in is going to be, and if we look at the top, we can work it out because we've got the total EMF and we've got the internal resistance, so we can work it through. So therefore we can work out what our total power in is going to be. Therefore we can say that the power dissipated in R is equal to the total power minus the wasted power. So you pop that all through and you get your answer to be 0.40 watts. Our next question shows us that a student uses two cells, each of EMF 1.5 volts and an internal resistance of 0.65 ohms to operate a lamp. The lamp is rated at 1.3 volts and 0.80 watts. Deduce whether this circuit provides the lamp with 0.80 watts of power at a potential difference of 1.3 volts. Assume that the resistance of the lamp is constant. So pause the video now, then unpause the video when you want to go through your answer. Right, so how could you work it out? So first, you make sure you've got to give a conclusion to this, and our conclusion is going to be that it is suitable. Now, the first thing you can do, there's two ways you can work it out. Either what you can do is work out the current that's required in the lamp. So we can say P equals IV, so therefore I equals P over V, so we can work it out because we've got that information from the lamp. So we know P is 0.80, we know V is going to be 1.3 volts, so we work out our current required to be 0.62 amps. We can then work out what our resistance of our lamp is going to be because you know R is equal to V squared over P, and therefore we can work out what the current in the cell is going to be, and therefore what we can do is say that lost volts is going to be equal to 0.65 times by 0.31, and you can work out your answer concluded as suitable. Or you could also do the idea that the terminal PD, which is going to be the PD in the circuit, is going to be 1.5 volts minus 0.2 volts, because we can work out the internal resistance to be the lost volts to be 0.2 volts from our internal resistance, and therefore we can work it out like that and conclude that the PD across the lamp is going to be appropriate enough to light it. Right, the next question says that the lamp operates at a normal brightness across a PD range of 1.3 to 1.5 volts. State and explain how more of these cells can be added to the circuit to make the lamp light at a normal brightness for a longer time. No further calculations are required. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this type of question? So you've got to firstly think to yourself, how are you going to add these cells, okay, to keep it at a normal brightness? Now you've always got to add them in parallel, because the more energy stored in the banks of the cells, okay, is going to mean that there's less power needed from each cell, whilst without increasing the voltage across the bulb. Now again, it's very important to remember that when you put cells in parallel, it won't actually increase the EMF going into the circuit, okay, so therefore it won't increase the terminal PD above 1.5 volts, so therefore they won't actually break. Now again, remember that in parallel you would say that the current is shared by the cells, so it takes longer to convert the energy stored in each cell, so it would work through correctly. Let's have a look at our next question. A battery of EMF 7.4 volts and negligible internal resistance is used to power a heating element inside a glove. The heating element has a resistance of 3.7 ohms. The designers state that the battery can produce a current of 2 amps in the heating element for 240 minutes. Calculate the energy dissipated in the heating element in this time. Then the length of the heating element is needed is about 0.85 meters. The designer considers using carbon fiber tape for the heating element, and you've got some information regarding this tape. Deduce whether the carbon fiber tape is suitable for making the heating element for the glove. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to think about what equation you want to do. Now, really, you think energy is equal to power times by time, and then what you can do is you can then use any of the information given to then work out what your power is. I mean, you could do P equals VI, P equals I squared R, P equals V squared over R, any one of those, then multiply by the time to get your answer out. Now, again, remember, we use time is in seconds, not minutes, so you can't use 240, you've got to convert it into actually seconds, so times 240 by 60. The next one, you've got to deduce whether this value is going to be long enough to actually make it work. So what you're going to have to do is you're going to have to use your resistivity equation of rho is equal to RA over L. Then you make L the subject, because you've got rho, you've got A, you've got R, and then you work out that L is going to be 0.91 meters, so therefore you need 0.9, so you have 0.91 meters. It says you need about 0.85 meters, so therefore you can make your conclusion based on that. Our next question says to us, a metal has a resistivity of 4.9 times 10 to the minus 7 ohm meters. Firstly, define resistivity, then secondly, a wire resistor of resistance 6.8 ohms is made from the metal. The diameter of the wire is 2.4 times 10 to the minus 4 meters. Calculate the length of the wire. So pause your video now, then unpause the video when you want to go through your answer. Right, in our first question, you've just got to know what the definition of resistivity is. You've just got to learn it. So resistivity is the resistance experience between opposite faces of a unit cube of a material, or you could say it's the resistance times by the cross-sectional area over the length, or you could say it's the amount of resistance that a material would have per meter that the charge carrier would travel through that particular material. Now, in our next question, you would say that resistance is equal to rho L over A. You then rearrange it to make sure that you have L to be the subject. So L is going to equal RA over rho. Now you've got R in the question, you've got rho in the top of the question. Now you're not actually given A, but you are given the diameter. So what you should be doing is getting the diameter, halving it to make the radius. Therefore you would say that area is going to be equal to pi r squared. Now we know this because it's a wire, so we're assuming that its cross-sectional area is circular, and you get your answer to be 0.63 meters. Our next question says a car battery has an EMF of 12.2 volts and an internal resistance of 0.015 ohms. A resistor of resistance 7.6 times 10 to the minus 3 ohms is connected directly between the terminals of the battery. Calculate the current in the resistor, then calculate the rate of heating inside the battery as soon as the resistor is connected between the terminals. So pause your video now, then unpause the video when you want to go through your answer. Right, so in this first question, what you're going to have to do is you're going to have to work out the current. Now you're given R in the question, and you're also given V in the question. Now it's important to note that when you're doing this, you've got to be careful about what value you're using for R. So because we're trying to calculate the current in the resistor, we're going to say I is equal to V over R, and remember that the total resistance we're going to be talking about is going to be the two added together. So it's the internal resistance and the resistance of the resistor. So you add the two together to get your R. You've got V, so you can work out what the current is going to be. Now again, what do you mean by say the rate of heating? So that's the power, because power is energy transferred over time, or the rate of energy transfer. So therefore P equals I squared R. Now why use I squared R? Well, because you've got I, because you've just worked it out, and you've got R from the question, pop the values in, and you're going to get your answer to be 4,400 watts. Now it's important to note that because we're calculating the heating inside of the battery as soon as the resistor is connected between the terminals, just be careful about what value of R you're going to be using. Okay, so what you should be doing is you should be doing your value of your current, okay, squared times by 0.015, because we're looking at just the internal resistance. Right, our next question shows us that a student has a 1.5 volt cell, a diode, an ammeter, a voltmeter, connecting wires, and a rheostat. Now a rheostat can be used as either a variable resistor or as a potential divider. So show your circuit where the rheostat is used as a variable resistor, then draw a suitable circuit to show your rheostat as a potential divider, then explain the advantage of using a rheostat as a potential divider rather than a variable resistor. So pause the video now, then unpause the video when you want to go through your answer. Now, the first thing to note, it's very important to understand that you've got, when you're using a rheostat as a variable resistor, as shown here, that it's going to be in series with the actual device that it's with. So therefore, we're going to have our variable resistor in series there with our diode. So just to clarify, the other trick you've got to remember is that it's going to have to be in the same direction as the diode, because otherwise, if you haven't got the same direction, the circuit won't actually work, so it wouldn't be suitable. Again, remember, ammeter goes in series, voltmeter goes in parallel with the thing that you're measuring, which is the diode, so the voltmeter goes in parallel with the diode. Now, if we wanted to use our rheostat as a potential divider, now you can see there's a bit of a difference. So now what we do is we place it in parallel with our diode. So what we've got is our rheostat is feeding into our diode as such. Remember, our ammeter is going to measure across the two because we want the current in the circuit, and then the voltmeter is still in parallel with the diode. Now you've just got to learn why we'd sometimes have our rheostat as a potential divider, and the fact is, when you've got your rheostat as a potential divider, the PD across the diode can go to 0 volts, or you can get the full measurements of potential difference, means the same thing, because when you've got in this case, you can actually take all the potential difference from the diode to the rheostat. Now that'll never happen when they're in series, because when they're in series they'll ratio with each other, so they'll always have a certain amount for each one. The next question shows that figure 2 shows a circuit containing 2 fixed resistors, a variable resistor and a battery with negligible internal resistance. So you've got voltmeter 1 and voltmeter 2 connected across fixed resistors, and the resistance of the variable resistor is increased. So what will happen to the readings on V1 and V2 when they're affected by this change? So pause the video now, then unpause the video when you want to go through your answer. Right, so let's just talk about V1 first. So if you increase the resistance of the variable resistor, well, it's important to know that V1 is going to go down. V1 is going to go down because you'll notice that the variable resistor and the resistor across V1, they're a potential divider, so they're linked to each other. So the total EMF from that battery is going to be split between these two. So if the resistance of the variable resistor increases, that will increase the potential difference it takes, because V equals IR. I stays constant, so if R goes up, V goes up. Now because it splits between the two, if V goes up for the for the variable resistor, well, therefore it's going to go down for the resistor, because they've got to share them out. Now if you look on the circuit, V2 is going to stay the same because that's in a different parallel branch, and parallel branches are independent of each other. So therefore, if the variable resistor changes its resistance, and therefore the PD it takes out from that parallel branch, it will just not affect that particular circuit. Our next question shows figure 8, which has shows bulb X connected to 2 other lamps, Y and Z. Now all 3 lamps have identical IV characteristics. So explain for this circuit how the resistance of Y compares with the resistance of X. You don't need to do any calculations. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, you've got to understand what's happening in this circuit. So X is just in series, while Y and Z are parallel with each other. So the first thing to note is that when you go past X and you split between Y and Z, the current is going to split between the two. So therefore, less current is going to pass through Y. So therefore, you're going to say that Y is going to have less voltage. Now, because it's got a lower current and a lower voltage, the resistance of Y is going to be less. So Y has a lower resistance. You also could be aware of this because it's in parallel with another bulb of identical characteristics, and when you've got multiple paths, the resistance going through that particular component will decrease. Our next question shows an IV characteristic of a filament lamp. So firstly, explain how figure 2 shows that the filament lamp is not an ohmic conductor, and explain in terms of the particles in the filament why the filament is not an ohmic conductor. So pause the video now, then unpause the video when you want to go through your answer. So how do you answer this particular question? Right, so when you're answering this particular question, you've got to understand what we mean by an ohmic conductor. So an ohmic conductor is a conductor where I and V are directly proportional to each other. So because it's not a straight line through the origin, they're not directly proportional to each other, so therefore that's not an ohmic conductor. Now, why in terms of particles is it not an ohmic conductor? Well, when you increase the potential difference, you're increasing the temperature of our actual material. So therefore, resistance is caused by the electrons colliding with the lattice of the filament. Now, if you increase the temperature, the vibrations of the ions will increase. So they'll vibrate further. So therefore, there's more chance of a collision. So therefore, our resistance and temperature increase. Now our next question looks at a circuit designed by a student to monitor temperature changes. The supply has a negative internal resistance and the thermistor has a resistance of 750 ohms at room temperature. The student wants the output potential difference at room temperature to be 5 volts. The 0.25 kilo ohm resistor is made of 50 turns of wire that is wound around a non-conducting cylinder of diameter 8 millimeters. The resistivity of the wire is 4.2 times 10 to the minus 7 ohm meters, so determine the area of the cross-sectional wire that has been used for the resistor. So pause your video now, then unpause the video when you want to go through your answer. Well, for this one, because we're trying to work out the area of the cross-sectional wire, okay, and we need to therefore use this particular understanding to then work out what's going to go on, the first thing we need to know is we're going to be using the equation that rho is equal to RA over L. But what we want to do is rearrange it to make A the subject. So A is therefore equal to rho L over R, but you're not actually given L in the question yet, but what you are told is that there's 50 turns of wire round a cylinder of a cylinder with a diameter of 8 millimeters. So you then use that idea to work out what your length of the wire is going to be, which is the circumference of the cylinder multiplied by 50 turns. So you'd work out what our circumference was by doing pi d there, and then you would work that through. Then you would multiply by 50 to get a length of 1.26 meters, and then rearrange it to then put L in the subject, then work out area like that. Now our next question says the student selected a resistor rated at 0.36 watts for the 0.25 kilo ohm resistor. So determine whether the resistor is suitable, then determine the value of R that the student should select. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first question, what are we aware of? That the maximum possible PD across the 0.25 kilo ohm resistor is 9 volts, because if you look, that this resistor is going to be in a potential divider circuit with this parallel combination. So the maximum possible PD it could draw is 9 volts, the entire EMF of the battery. So therefore the maximum possible power you can dissipate is P is equal to V squared over R. Now we know R is 250 ohms, that's what 0.25 kilo ohms is. Then we can say P is equal to 9 squared, the total possible voltage, 9 squared over 250, which is 0.32 watts. So it's asking whether this resistor is going to be suitable. Now it will be suitable because it's rated at 0.36 watts. It's going to be therefore, okay, below 0.36 watts, so therefore it's not going to be possible for that. Now the next one is asking about determine the value of R that the student should select. So firstly, what you've got to do is, if you look at this circuit, R and the thermistor are in parallel with each other. So you've got to remember you've got to use the parallel equation for resistors. So you know that 1 over RT is equal to 1 over R1 plus 1 over R2. So therefore we can use that to work out what the resistance is going to be. So we should hopefully be aware that if we know what that the thermistor has a resistance of 750 ohms, okay, and we know, okay, that in this instance that we want our total to be 0.313 kilo ohms, so therefore we can work it out that it's going to be 450 ohms in total. Then we also can do that our current in the circuit at room temperature is going to be 4 over 250. So therefore what we know is we know that current, okay, so we know V equals IR, so therefore I is equal to V over R. We know R is going to be 250 ohms in terms of the resistor, which is the 0.25 kilo ohm resistor. We know that V in this instance is going to be 4, okay, because we're aware of what it should be, because we want the total power output to be 5 volts. So therefore if the output of the parallel combination is 5, well therefore in the resistor it's going to have to be 4, because 5 plus 4 equals the total, which is 9. So therefore we know that the current is going to be 16 milliamps. So therefore we can say that therefore the current in the thermistor is going to be 6.7 milliamps, because in this instance it's going to be 5 is going to be our value for our volts. We know that our R is going to be 750 ohms. Okay, we know that because that's what the thermistor's resistance tells us in the question. So therefore therefore the current in the thermistor is 6.7 milliamps or milliamps, yeah. So that if we know that the current in the thermistor is 16 milliamps and then it splits up into two, and the thermistor is taking 6.7 milliamps, well therefore the current in the resistor is going to be 9.3 milliamps because that's taking the difference. So therefore we know that the current is going to be 9.3 milliamps. We therefore know that the voltage is going to be 5 volts because we know that from the question. So R in this instance is 5 over 9.3 times 10 to the minus 3 because we're in milliamps. So therefore it's 540 ohms. So either way will give you your answer of what the resistor should be. Now also please do remember that you should give your answer to 2 sig figs. Why is that? Because in the question you're given your values to 2 sig figs, 9.0, 0.25. They're all values given to 2 sig figs. Right, our next question shows figure 9, which is a practical circuit in which a variable resistor is used to control the brightness of a lamp. The voltmeter reading is monitored as the variable resistor is adjusted to make the lamp brighter. Explain why the reading on the voltmeter decreases as the brightness of the lamp increases, and then the variable resistor is adjusted so that the lamp is at its brightest. The reading V1 on the voltmeter is noted. A second identical cell is then connected in parallel with the cell in figure 9. The new reading V2 on the voltmeter is noted. Explain why V2 is greater than V1. So pause the video now, then unpause the video when you want to go through your answer. So how do you answer this particular question? So in this first question, what's very important is as follows. Okay, we've got to think about the voltmeter decreasing when the brightness of the lamp increases, and look at how they're connected in the circuit. So you'll notice that straight away, that the lamp and the variable resistor are connected as a potential divider. So what's important to note, is that as the brightness of the lamp increases, so therefore the current through the lamp increases, so therefore it tells us that our internal resistance is a larger proportion of the total resistance, because if there's an increase in the lost volts across the internal resistance of the cell. So it's important to note that idea. So therefore our ratio of internal resistance to external resistance is larger. We're getting a bigger value of our internal resistance. So what's going to happen is the read on the voltmeter is going to go down, because literally there's less PD in that circuit now, because our brightness of our lamp is bigger. Now the second one, the variable resistor is adjusted to the lamp's at its brightest. The V1 is noted. A second identical cell is connected in parallel. What's the new reading on V2, and why is it going to be greater in that instance? Well, our lost volts is going to be reduced, because the effective internal resistance is therefore a smaller proportion of the total resistance. Or you could also say that the two cells in parallel act as a single cell with the same EMF, but they've got half the resistance. Why have they got half the resistance? Well, now there's two possible paths for the charge to flow through the cells, so therefore there's less chance of the collisions because there's more paths, so therefore you're going to have less internal resistance in the cell. So therefore our proportion of internal to external resistance is smaller. Or you could also say that the current through each cell is less than a cell on its own, because each cell is going to have less current than if there's just one cell, because now there's two possible paths. So the decreased current through the cell will decrease the lost volts, or the potential difference across the internal resistance. So therefore we've got more PD in our circuit, because less is being wasted as lost volts inside the actual power source. So therefore our reading on our voltmeter is going to go up. So I hope you've enjoyed this particular revision session on electricity. If we've been successful on electricity, we should be able to answer A-level physics examination style questions, assess our own understanding on A-level physics, then understand what topics we need to improve upon for A-level physics. So thank you very much for watching this video on electricity, and have a lovely day.